In this lesson, we will look at a mechanical ice protection system, as used on the ATR 72 shown here. A mechanical system, using pneumatically inflated boots, may be employed on the wing and tail leading edges of certain types of piston engine and some modern turbopropeller aircraft. This type of system is used for de-icing. It removes ice that has already formed on the surface. It is switched on when there is an ice buildup of between 0.5 and 1.5 centimeters, depending on aircraft type. The de-icing boots, or overshoes, which are fixed to the leading edges of the surfaces to be protected, consist of layers of natural rubber and rubberized fabric, between which are fitted flat inflatable tubes closed at one end. The tubes are also made of rubberized fabric. In some boots, the tubes are so arranged that when the boots are in a position on a wing or tail leading edge, the tubes run along the leading edge. In others, they run across at 90 degrees to the leading edge. The boots may be attached to a leading edge either by screw fasteners or by cementing them directly to the inboard portion of the leading edge, where the wings are thickest. The tubes in the boot sections are inflated with air from the aircraft's compressed air system. This air may come from the pressure side of an engine-driven vacuum pump, from a high-pressure reservoir, or, in the case of some types of turbopropeller aircraft, from the engine compressor. The inflation weakens the bond between the ice and the boot surfaces, causing the ice to break away. At the end of an inflation stage of the operating sequence, and whenever the system is switched off, the air is sucked from the boots to hold them flush with the leading edge. The suction may be produced by a vacuum pump or by Venturi action. This inflation and deflation cycle is repeated during the period the system is in operation. When the system is switched off, suction is applied continually to all tubes of the boot sections to hold the sections flat against the leading edges, thus minimizing aerodynamic drag. This type of system has two drawbacks. Firstly, the boots disturb the airflow over the leading edge, increasing drag. And secondly, they are quite expensive to maintain, as the boots wear out relatively quickly and they are easily damaged and eroded. The de-icer boots are pulsated in a set cycle, the frequency of which can be varied by a frequency selector to cater for light or heavy icing conditions. To reduce the volume of pressurizing air required, the boots are usually divided into groups. For instance, Group 1 may be the port and starboard wing outboard boots. Group 2, the port and starboard wing inboard boots. And Group 3, the fin and tailplane boots. When the system is switched on, the boots will inflate and deflate in sequence. First Group 1, then Group 2, and finally Group 3. At the end of the cycle, there will be a time delay, which can be varied by the pilot, depending on the severity of the icing before the cycle starts again. The controls and indicators required for the operation of the system vary from aircraft to aircraft. In the basic arrangement, there will be a main on-off switch and a selector to allow the pilot to select the time between cycles, depending on the severity of the icing. There may also be pressure and vacuum gauges or indicating lights to confirm system operation. That is the end of the lesson. You should now understand that a mechanical system using pneumatically inflated boots is often used on modern turbo-propeller aircraft. You should know that it can only be used for de-icing purposes. You should also know that the two disadvantages of this type of system are that it is expensive to maintain and that it causes an increase in drag. In this lesson, we will look at thermal ice protection systems, as used on many turbojet aeroplanes, including the Boeing 737. A thermal ice protection system is one where the surfaces to be protected are heated. One major advantage of this system over mechanical systems is that there is no change in the profile of the surface being protected. This heat may be provided by hot air, electricity, or hot oil, although this method is rarely used. The most common method of thermal ice protection is the hot air system. There are several methods by which the heated air can be supplied, and these include the bleeding of air from a turbine engine compressor, the heating of ram air by passing it through a heat exchanger located in an engine exhaust gas system, and the heating of ram air by a combustion heater. The areas normally protected by a thermal system include the engine air intakes and compressor inlet guide vanes, plus the wing leading edges and slats if they are fitted. On some, but not all aircraft types, the tailplane and fin leading edges are also protected. In systems supplied with compressor bleed air, the hot air is tapped directly from the engine compressors. The air is normally taken from a low compressor stage and a high stage to ensure the temperature and pressure is sufficient at all engine speeds. The amount of air tapped off is a very small proportion of the total airflow through the compressor, so the effect on engine thrust output of using compressor air for ice protection is similarly very small. The bleed air temperature may be controlled by a pre-cooler using fan air before it passes into a bleed air manifold. From here, the air supply to the areas requiring ice protection is controlled by shut-off valves. In some systems, these valves are able to modulate to maintain the air pressure within acceptable limits. The exhaust gas heat exchanger method of supplying warm air is employed in some types of aircraft powered by turbo-propeller engines. The heat exchanger unit is positioned so that exhaust gases can be diverted to pass between tubes through which outside air enters the main supply ducts. The outlet temperature is usually regulated by a device, such as a thermostatically controlled flap, fitted in the ducting between the exhaust unit and the heat exchanger. In a combustion heating system, ram air is passed through a cylindrical jacket, enclosing a sealed chamber in which a fuel-air mixture is burned. The ram air is heated by contact with the chamber walls. Air for combustion is derived from a separate air intake and is supplied to the chamber by means of a blower. The combustion heater is fully explained in the pneumatic systems lesson. The hot air systems used for airframe ice protection on modern turbojet aircraft generally use engine bleed air and are normally anti-icing systems. In systems of this type, hot air is supplied to a pipe or duct running along the inside of the leading edge sections to be protected. These ducts are known as spray or piccolo tubes. The duct has spray holes in it, through which air is allowed to escape and heat the leading edge, melting any ice that has formed and preventing further ice formation. The air is then ducted rearwards before being dumped overboard through holes in the lower surface. The system is controlled by flight deck switches, which operate valves in the pneumatic manifold to shut off the airflow when ice protection is not required. Engine air intake de-icing or anti-icing can be achieved either using hot bleed air or an electrical resistance heating system. Electric heating is usually only found on propeller-driven aircraft, where the propeller is also de-iced by electric heat. On other types, electricity is usually only used to heat smaller components, such as windscreens and pitot heads, because of the high currents required. A typical hot air engine ice protection system is shown here. The air is tapped from the compressor at a suitable point. It passes through an electrically operated control valve, which is actuated by a switch on the flight deck. The air heats the inlet guide vanes, the nose cone, and the air intake cowl. The air is then exhausted either to atmosphere or back into the air intake. In an electrical heating system, heating elements, either of resistance wire or sprayed metal, are bonded to the air intake structure. The electrical power supply required for heating is normally a three-phase alternating current. In the electrical wire type of system, the elements are sandwiched between layers of glass cloth, impregnated with resin. In some systems, the elements may be sandwiched between layers of rubber. The outer surfaces are, in all cases, suitably protected against erosion by rain and the effect of oils and gases. In the sprayed metal system, a base insulator is brushed directly onto the surface to be protected, and then the electrically conductive metal is sprayed onto it. A further insulating layer is applied on top of this. The outer surface is then given a suitable protective coating. The resulting protected surface is known as a spray mat. In an electrically heated ice protection system, both anti-icing and de-icing techniques are employed by using both continuously heated and intermittently heated elements. The system is controlled by switches on the flight deck. When the control switch is placed to on, the power supply is fed directly to the continuously heated elements, and via a cyclic time switch unit to the intermittently heated elements. The cyclic time switch unit controls the application of current in selected time sequences, compatible with prevailing outside air temperature conditions and the severity of the icing. In this example, the output of the time switch can be changed by selecting either light or severe icing conditions. The cyclic circuit is arranged so that while the supply is on for some heaters, it is off to others, and vice versa, in order to maintain a constant de-icing load to the electrical system. A number of small components are electrically heated to prevent ice formation. These and the windscreens are the only items normally electrically heated on large turbojet-type aircraft. Some of them, such as pitot heads, angle of attack sensors, and temperature probes, may have switches and warning lights in the cockpit. Others, such as wastewater drain mast heaters and the inline heaters fitted to water pipes, operate whenever the aircraft's electrical system is powered. That is the end of the lesson on thermal ice protection. You now know that the heat source for thermal systems can be hot air, electrical power, or, very occasionally, hot engine oil. You should understand that airframe ice protection on modern turbojet aircraft is normally achieved using hot air bled from the engine compressors, with very little loss of engine thrust. These systems are usually anti-icing systems. You also now know that the engine intake can be heated using either hot air or electrical power. If hot air is used, the system will be an anti-icing system. But if electrical power is used, there will usually be a combination of de-icing and anti-icing. Finally, you should know that on turbojet aircraft, electrical power is normally only used to heat the windscreens and smaller surfaces and components. In this short lesson, we will look at fluid-type airframe ice protection systems, as used on the Hawker 800 aircraft. A fluid or weeping wing system works on the principle of forming a film of glycol-based freezing point depressant fluid over the surfaces to be protected. This film of de-icing or freezing point depressant fluid combats ice formation by both melting the ice and by preventing adhesion of any ice crystals. Hence, the system can be operated in a de-icing or anti-icing mode. A typical system will contain a storage tank, a pump, and a network of pipes to transport the fluid to the required locations. The pipes terminate at distribution panels fitted along the leading edges of the surfaces to be protected. The distribution panels have porous outer panels on the leading edge of the aerofoil. The fluid is pumped into the cavity between the porous outer panel and a backing plate. It seeps out through the porous panel and is then distributed over the aerofoil surface by the airflow. The major drawback of this type of system is that the system's operation is limited by the amount of fluid in the storage tank. And, of course, the greater the amount of fluid carried, the greater is the weight penalty for carrying it. In this lesson, we will look at the various ice and rain protection systems available for aircraft windscreens. Windscreens are protected from icing by fluid sprays or by electrical heating. Cabin air may also be blown across them for demisting. Wipers and washers are also provided. And on some aircraft, these may be assisted by the use of rain repellent systems. We will now look at these systems in more detail. Independent two-speed wipers are usually provided for the pilots. They may be electrically or hydraulically powered and are controlled by switches on the flight deck. They normally have a parking facility. When the switch is placed to off, the wipers will park at the bottom of the screen. Windscreen wipers should not be operated on a dry windscreen. The windscreen washer system sprays washer fluid onto the windscreen panels and is used in conjunction with the wipers to clean the windscreens. A typical system consists of a fluid reservoir, an electrically driven pump, and pipes feeding the fluid to spray jets below the windscreens. A single washer button controls the fluid for both screens. There are two types of rain repellent system in common use. In one, the windscreen is given a permanent hydrophobic or water repellent coating during manufacture, which causes the water to form large beads and roll off the surface. In the other, a temporary fluid coating is applied to the screen when required. Rain repellent fluid should only be applied to the screen during very heavy rain. In a typical fluid rain repellent system, there will be a nozzle for each screen and a manifold which stores and distributes the fluid to the nozzles. The manifold is charged with repellent fluid from an aerosol-type disposable container which screws into it. Electrical time-controlled solenoid valves control the flow of fluid to the nozzles. Rain repellent fluid is sprayed onto the respective windscreen by momentarily pressing the rain repellent button switch on the captain's or first officer's wiper control panel. Each actuation of the switch opens the valve for a preset period of time, regardless of how long the switch is held in. The repellent reacts with the water, increasing the size of the water drops, which are then blown off the screen by the airflow. Depending on airspeed and rain intensity, each actuation should be adequate for 2 to 5 minutes of repellent action. Rain repellent fluid must not be applied to a dry windscreen, as it will reduce visibility. The method employed in a fluid windscreen de-icing system is to spray the windscreen panel with a methyl alcohol-based fluid, which will melt any ice that has formed. The principal components of the system are a fluid reservoir, a pump, which may be a hand-operated or electrically operated type, supply pipelines, and a spray tube unit. Here, we show a typical aircraft system in which fluid is supplied to the spray tubes by an electrically operated pump. Electrical windscreen heating systems are almost always anti-icing systems. Windscreen heat is used from takeoff until landing because the heat increases the flexibility of the screen and hence its resistance to damage from bird strikes. A heated windscreen is of a laminated construction. In the typical example shown here, the film-type resistance element is sandwiched between a hard glass outer coating and a thick clear vinyl panel or interlayer. There is another hard glass panel on the inside of the screen. There are two types of electrical windscreen heating systems in common use. One system has a temperature sensor attached to the windscreen, and the other has a temperature-sensitive switch. Both are controlled and monitored by cockpit switches and warning lights. In both types of system, the resistance element is heated by alternating current or AC supplied from the aircraft's electrical system. The power required for heating varies according to the size of the panel and the heat required to suit the operating conditions. Air from the air conditioning system can be blown across the inside of the screen for demisting purposes. In the system using a temperature sensor in the windscreen, the sensor sends temperature signals to an electronic controller. The controller varies the current flow to the windscreen to maintain it at a constant temperature. This is typically around 30 degrees Celsius in flight, and a lower temperature, typically 16 degrees, on the ground. The changeover is made by the landing gear air-ground logic system. This system has the advantage of keeping the thermal gradient or temperature difference between the inside and outside of the screen to minimum, thus increasing the useful life of the screen. In the other system, temperature-sensitive switches or thermostats are fixed to the windscreen. When the screen reaches the required temperature, the thermostat opens, switching off power to the screen. When the screen cools again, the thermostat closes, reapplying power. In addition to the normal temperature control circuit, this type of system usually has incorporated in it a circuit which supplies more heating power under severe icing conditions when heat losses are high. When the higher power setting is selected, the supply is switched to a higher voltage output, thus maintaining the normal operating temperature. Both systems also have a thermostat in the windscreen for overheat protection. If the normal system fails to control the windscreen temperature, the overheat thermostat will cut off the power and put on a warning light. On some systems, the system will now operate in the overheat mode, with the overheat thermostat controlling the temperature and the warning light cycling on and off. On others, once the overheat thermostat opens, the warning light is locked on and heat can only be reapplied by cycling the control switch to off and then back to on. If the windscreen should overheat, then it may suffer permanent damage to the vinyl interlay. This will manifest itself as vinyl bubbling and discoloration. That is the end of the lesson. You have learned that windscreens can be protected from icing by fluid sprays or by electrical heating. Remember that electric heating of windscreens increases their impact resistance, so it is kept switched on from takeoff until landing. Remember also that cabin air may be blown across the windscreens for demisting purposes. You now know that wipers are used to clear rain from the screen. Remember that they should not be used on a dry windscreen. On some aircraft, the wipers may be assisted by the use of rain repellent systems. Bear in mind that rain repellent fluid should only be used in very heavy rain, and that it must not be used on a dry windscreen. In this lesson, we will look at how engine propellers are protected from the effects of icing. Ice formation on a propeller blade produces distortion to the aerofoil section, causing a loss in efficiency and possibly causing unbalance, which can lead to destructive vibration. The build-up of ice must be prevented, and this is usually done by electrically heating the propeller blades. Because of its thickness and lower speed, the inner third of the propeller blade is most susceptible to icing, and is always de-iced. In some installations, the middle third is also de-iced. The outer third of the blade is not so susceptible to icing, and is not normally de-iced. The electrical heating elements are usually fitted in components known as overshoes or boots. The construction of the overshoes varies between propeller types. In a common installation, the heating element wires are interwoven with glass threads, which form a glass cloth base, which is cemented between sheets of rubber. A protective guard of wire gauze is cemented beneath the outer rubber covering. The overshoe is shaped to fit around the blade leading edge and is cemented to it. In the case of turbine engine propellers, the cover over the pitch change mechanism, or the spinner as it is known, may also have electrical heating elements embedded in it. Depending on the type of aircraft, the electrical power for heating the elements is either direct or alternating current. These systems consume a relatively high amount of electrical power. However, they are controlled by employing a cyclic timer, which will de-ice the propeller blades of one engine at a time, thus reducing the power requirement. In some installations, a power relay is fitted in the engine nacelle. It allows the length of heavy high current wiring to be kept to a minimum, with light cable being used in the control circuit. In turbopropeller engine installations, the propeller heating circuit may form part of a power unit de-icing and anti-icing system, with the cyclic control being integrated with the engine air intake heating circuit. The power required for heating is conveyed to the elements via cables, slip rings, and by brushes, contained within a brush block housing. Slip rings and brushes are components used to transfer electrical power from a stationary part to a rotating one. They are fully explained in the Electric Systems series of lessons. In icing conditions, during the unheated period, a thin film of ice will build up on the leading edges of the propeller blades. Before this film builds up sufficiently to interfere appreciably with the aerodynamic characteristics of the blades, the cyclic control applies heating power. The ice in contact with the blade surfaces melts, breaking the bond between the ice and propeller blade. The remaining ice is then carried away under the action of centrifugal and aerodynamic forces. That is the end of the lesson on propeller ice protection. You should now know that electrical propeller de-icing is usually done cyclically, and that on turbopropeller type aircraft it may be integrated with the engine ice protection system. In this lesson, we will look at the provisions made to help the crew and passengers escape from the aircraft in an emergency. The number of emergency exits that an aeroplane requires is stipulated in the regulations. It varies with the number of passenger seats and the types of exit fitted. The requirements are shown on the table on the screen, but are not required knowledge. However many emergency exits are required, before an aeroplane with a seating capacity of more than 44 passengers can be certified, it must be demonstrated that all occupants, including passengers and crew, can be evacuated from the aeroplane using a maximum of half the exits in the dark in 90 seconds or less. Emergency exits may be passenger doors or removable panels or hatches. Or for the flight crew, they may be opening windows, direct vision windows, or a roof hatch. The regulations related to doors and other emergency exits are contained in EASA document CS25. The following is a summary of the regulations. All emergency exits, except the pilot's windows, must be openable from both inside and outside of the aeroplane. In the event of an emergency, they must be capable of being opened within 10 seconds. To aid identification, all emergency exits must be outlined externally by a 5 cm band in a contrasting colour. If a lockable door is fitted to the flight crew compartment, then suitable emergency exits must be provided, so that neither passengers nor crew members need to use the door in order to reach their designated emergency exits. If the aircraft capacity is over 20 seats, then flight crew must have their own emergency exit provision. This can be either one exit on either side of the flight deck, normally these are direct vision windows, or a single hatch in the roof. Each passenger emergency exit must be indicated by a sign, visible to the occupants approaching along the main aisle or aisles, and all emergency exits must be kept clear of any obstruction during flight. Each passenger emergency exit, its means of access, and its means of opening must be conspicuously marked. The operating method must be simple and obvious, and the exit must be capable of being opened in 10 seconds or less. The location of each passenger emergency exit must be recognizable from a distance equal to the width of the cabin. A means must be provided to assist the occupants in locating the exits in conditions of dense fog, smoke, or darkness. This is covered in the emergency lighting lesson. All passenger doors fitted in the side of the fuselage are considered to be emergency exits. Doors may be electrically or manually operated. In the case of electrical operation, there must be a manual override system, possibly with spring assistance, to ensure the doors can still be opened in 10 seconds in the event of electrical failure. In the particular door shown here, it is normally opened and closed using the push buttons. But in the event of an electrical failure, the manual handle can be pulled, allowing a compressed spring to open the door. There must be a means to lock and safeguard each external door against opening in flight. This can be done using an automatic system, which will lock and unlock the doors as the weight of the aircraft is taken by the wheels. Each door must be fitted with a warning system in order to alert the crew when it is not fully closed and locked. This Airbus display shows locked-closed doors in green and open doors in amber. Interlocks may be fitted between the door locks and the aircraft's pressurization system to prevent the doors being opened until the aircraft is fully depressurized. Escape hatches may be located in the passenger cabin over the wings. These are normally plug-type hatches and are held in place by mechanical locks and aeroplane cabin pressure. The hatches can be opened from the inside or from the outside of the aeroplane. A seat back blocking an exit may be pushed forward by applying force to the top of the seat back. For safety reasons, hatches should not be removed in flight. On some aircraft, hatch removal may illuminate the over-wing emergency exit lights on the same side. If an escape slide is fitted, it will also automatically deploy when the hatch is removed. Some aircraft have escape straps stored in the overwing emergency escape hatch frame. The overwing escape hatch must be removed to expose the strap. One end of the strap is attached to the hatch frame. The other may have a clip on it to hook onto an anchor point on the wing. The escape strap can be used as a handhold in a ditching emergency to help passengers walk out onto the wing and step into a life raft. There are a number of regulations designed to ensure that escape through the emergency exits will not be hampered by their height above the ground. Each emergency exit, which is more than 6 feet, or 1.83 meters above the ground, with the aeroplane standing on its landing gear, must have a self-supporting slide to assist the aircraft occupants in descending to the ground. For aeroplanes for which a type certificate was first applied for on or after 1st of April 2000, there is a further regulation which requires that if, after the collapse of, or failure to extend of, one or more legs of the landing gear, any emergency exit, which now becomes more than 6 feet or 1.83 meters above the ground, must also have a self-supporting slide to assist the aircraft occupants in descending to the ground. These regulations only apply to overwing exits if the edge of the wing is more than 6 feet or 1.83 meters above the ground. The regulations also apply to flight deck emergency exits. However, the flight crew escape means may be a rope attached at one end to the fuselage, or inertia reels similarly attached to the fuselage. The regulations relating to evacuation assistance are now being displayed on the screen. Spend a moment familiarizing yourself with them before moving on. Emergency escape slides are inflatable units with integral carbon dioxide cylinders used to inflate them. Because of the size of the slides and the amount of gas required to inflate them, some systems use devices known as aspirators, which suck in outside air to supplement the carbon dioxide in the inflation process. When not required for emergency use, the escape slides are stowed in compartments on the bottom inner face of the passenger doors. There is a carbon dioxide cylinder pressure gauge visible through a cutout in the stowage container. The door slides incorporate a retaining bar, known as a girt bar. It is fixed to the top of the slide. The girt bar can be in one of two positions. It may be either fixed to the cabin floor or free to move with the rest of the slide. It is the position of the girt bar which governs whether the slide will deploy or not when the door is opened. If the door is opened with the girt bar attached to the floor, the slide will be dragged from its container by the door opening action. The automatic inflation system will then inflate the slide. However, if the door is opened with the girt bar free to move with the slide, then the slide will remain in its container. The girt bar is fastened to the cabin floor from when the aircraft leaves the stand at the start of a flight until it returns to the stand at the end, so that in the event of an emergency, the slide will deploy when the door is opened. The bar is disconnected from the floor prior to the door being opened to allow passengers to embark and disembark. In the simplest system, the girt bar is moved manually into and out of the cabin floor attachment points by a cabin crew member. On most modern aircraft, the girt bar is positioned by operation of a two-position slide lever, either on the door or on the cabin wall adjacent to the door. The two positions are marked manual or detach. and automatic or engage. With the lever in automatic or engage, the girt bar is fastened to the cabin floor and the slide is armed to deploy if the door is opened. If the lever is placed to manual or detach, then the girt bar is free to move with the slide and the door can be opened normally. If an attempt is made to open the door from the outside with the slide lever in the automatic or engage position, the lever will automatically move to the manual or detach position, thus preventing slide deployment and possible injury to the person opening the door. If the slide fails to automatically inflate when it is deployed, a backup inflation handle located at the top of the slide can be pulled in an attempt to release the carbon dioxide and inflate the slide. In the event of a landing on water, many large aircraft use the escape slide as a survival raft, with space for up to 60 people. To use the slide in this way, it is activated as before, and then can be released from the aircraft by pulling the slide release handle, which can be found under a cover at the top of the slide. The use of slides as life rafts is fully covered in the first emergency equipment lesson. In the event that the nominated emergency exits are blocked or are unable to be opened, supplementary escape routes, which can be broken into by the fire services from outside the aircraft, may be available. These take the form of cut-in or break-in areas. Cut-in areas are rectangular in shape, marked by red or yellow-coloured 3 cm wide right-angled corners. The markings are outlined in white if a contrast is required. Cut-in areas are not weak points on the fuselage structure, but areas under which no control runs, electrical looms, or stringers exist. That is the end of the lesson. You should take the following key points from it. The emergency exits on transport aeroplanes must allow all passengers and all crew members to leave the aeroplane within 90 seconds through 50% of the available emergency exits in the dark. Emergency exits must be able to be opened in 10 seconds or less. All emergency exits must be outlined externally by a 5 cm band in a contrasting colour. Cut-in areas are rectangular in shape, marked by red or yellow-coloured right-angled corners, and outlined in white if a contrast is required. Emergency exits, which are more than 1.83 metres or 6 feet above the ground with the aeroplane standing on its landing gear, or for aeroplanes for which a type certificate was first applied for on or after 1st of April 2000, after the collapse of, or failure to extend of, one or more legs of the landing gear, must have a self-supporting slide to assist the aircraft occupants in descending to the ground. Slides are inflated by integral carbon dioxide cylinders, supplemented by outside air. If an attempt is made to open a door from the outside with the slide lever in the automatic or engage position, the lever will automatically move to the manual or detach position. If the aircraft capacity is over 20 seats, or there is a lockable door to the flight deck, the flight crew must have their own emergency exit provision. In this lesson, we will look at the EU regulations appertaining to aircraft emergency lighting systems, and we will see how these regulations are put into practice. The basic regulations are laid out in EU OPS 1, Commercial Air Transportation, Aeroplanes, with greater detail being provided in CS 23, Normal, Utility, aerobatic and commuter category aeroplanes, and CS-25, large aeroplanes. The regulations split aeroplanes into 3 groups: those which have an approved passenger seating configuration of 9 or less, those with 19 or less but more than 9, and those with more than 19. With an approved passenger seating configuration of 9 or less seats, the aeroplane must not be operated at night unless it is provided with a source of general cabin illumination to facilitate evacuation of the aeroplane. This may use normal internal lighting systems, provided they are capable of remaining operative after the aeroplane's battery has been switched off. All aeroplanes with an approved passenger configuration of more than 9 seats must have an emergency lighting system with an independent power supply. For aeroplanes with an approved passenger configuration of 19 seats or less, but more than 9, which are not certified to EASA CS-23 or CS-25, the independent emergency lighting system must include general cabin illumination. For aeroplanes with an approved passenger configuration of 19 seats or less, but more than 9, which are certified to EASA CS-23 or CS-25, the independent emergency lighting system must include general cabin illumination, internal lighting in emergency exit areas, and illuminated emergency exit markings and location signs. Aeroplanes with an approved passenger configuration of more than 19 passenger seats must have an independent emergency lighting system which includes general cabin illumination, internal lighting in floor-level emergency exit areas, illuminated emergency exit markings and location signs, floor proximity emergency escape path markings in the passenger compartment, and exterior emergency lighting at all passenger emergency exits. We will now look in greater detail at the requirements for aeroplanes with more than 19 passenger seats. By doing this, the requirements for the other groups will also be covered. There must be an independent emergency lighting system. To achieve this, the emergency lights are normally battery operated. The batteries are usually of the nickel-cadmium type. They are normally kept fully charged by the aeroplane's electrical system. The batteries must be able to maintain the emergency lights at full brightness for a minimum of 10 minutes. General cabin illumination may be provided by white lights in the ceiling along the aisles and at the emergency exit locations. There may also be white lights located low down on the sides of the passenger seats to illuminate the escape paths. Exit location signs must have red letters on a white, electrically illuminated or self-illuminated background. The emergency exit signs must be repeated at low level. There must be floor proximity markings to provide emergency evacuation guidance for passengers when all sources of illumination more than 1.2 meters or 4 feet above the cabin aisle floor are totally obscured. These may consist of locator lights on the floor down the aisles, or a continuous strip of light along the aisle. Finally, there must be exterior lighting at all emergency exits, such that the escape route from the exit to the point on the ground where the evacuee will take his first step, is illuminated. The emergency lighting system is controlled by two switches. One on the flight deck and the other in the passenger cabin adjacent to a cabin crew member station. The flight deck switch has three positions: off, armed and on. It is guarded to the armed position. The switch is in the guarded arm position for all normal flight operations. Adjacent to the flight deck switch, there is a warning light which is captioned "Not Armed". This light is supplied from the normal aircraft electrical power supply and will come on at any time the aircraft electrical power supply is on, and the emergency lights are anything other than armed. The passenger cabin switch has two positions, normal and on. It is usually in the normal position. With the flight deck switch in the arm position and the cabin switch in the normal position, the emergency light control circuit is armed. It is monitoring the aircraft's essential electrical system, and provided this system is normal, the emergency lights will be extinguished. If the aircraft's essential electrical power system fails, the emergency lights will illuminate automatically. If the flight deck switch is moved to on, the emergency lights will come on. And because the system is no longer armed, the not armed light will illuminate. The pilot switch off position is used when shutting down the aircraft. With the switch in this position, the emergency lights will not automatically come on when electrical power is removed. With the pilot switch in the off position, the not armed light will be lit until electrical power is removed. The emergency lighting system may be switched on from the cabin switch by moving it from normal to on. Operation of the cabin switch to on will turn on the emergency lights no matter what position the flight deck switch is in. The selection of emergency lights on from the passenger cabin will illuminate the not armed light on the flight deck. That is the end of the lesson. Remember that the emergency lighting system has an independent power supply, which must be able to maintain the emergency lights at full power for a minimum of 10 minutes. The lights can be armed to come on automatically in the event of an essential electrical system failure, or they can be switched on manually from either the flight deck or the cabin. Emergency lights illuminate the emergency escape paths both inside and outside the aircraft. In this introductory lesson on oxygen, we will look at why oxygen may be required in an aeroplane, and we will examine the dangers that the carriage and use of oxygen brings. We will also discuss the safety precautions that are employed to reduce these dangers. In order for the body to function satisfactorily, it requires oxygen, which it extracts from oxygenated blood provided by the lungs. As altitude increases, the pressure of the air decreases, and the partial pressure of the oxygen in the air decreases proportionally. If there is insufficient oxygen entering the blood because of this reducing partial pressure, with increased altitude the body will become affected by a condition known as hypoxia. Below about 10,000 feet pressure altitude, normal breathing will provide adequate oxygen to combat hypoxia. Between 10,000 and 33,700 feet, a mixture of air and pure oxygen needs to be provided. Between 33,700 and 40,000 feet, 100% oxygen is required. And above 40,000 feet, oxygen under pressure has to be provided. Below 10,000 feet, the body is not affected very much by the slight reduction in the partial pressure of oxygen. And indeed, many people in the world live happily up to a height of 12,000 feet without suffering hypoxia. There will be some impairment of night vision as altitude increases towards 10,000 feet. Between 10,000 feet and 15,000 feet, the onset of hypoxia has more serious consequences. The heart rate increases and judgment is impaired. Short-term memory is lost at about 12,000 feet. Tasks become more difficult, and without supplementary oxygen in this altitude band, crew and passengers may become drowsy. Because the hemoglobin, which is the component of the blood which carries oxygen, is becoming deoxygenated, fingertips and lips will start to turn blue. Between 15,000 and 20,000 feet, the autonomic system cannot compensate, and the effects of hypoxia become more extreme, but are still imperceptible. Symptoms include euphoria, dizziness, headache, sleepiness, and further loss of judgment and performance. Vision may become tunnelled. Above 20,000 feet, performance decreases dramatically, with disorientation, confusion, and ultimately brain damage and death. A pressurized cabin with the cabin altitude maintained below 8,000 feet will prevent the onset of hypoxia. However, crews should always remain aware of the early symptoms of hypoxia, as a slow loss of pressurization can go unnoticed until it is too late. In the event of a sudden loss of pressure at high altitude, the onset of hypoxia will be very rapid. Following sudden decompression, for instance the loss of a window, there would, depending on altitude, be only a few seconds during which the pilot would remain at a level of consciousness where he could carry out effective actions. This is known as the time of useful consciousness. It is shorter than the time before he becomes unconscious. It is worth studying this table, which shows the time of useful consciousness if a decompression were to occur. For example, during a progressive decompression, the time of useful consciousness, while engaged in moderate activity at 30,000 feet, is 45 seconds. As soon as the symptoms of hypoxia are recognized, oxygen should be used, and the aircraft descended to an altitude where atmospheric oxygen is present in sufficient quantities to meet the body's needs. The regulations governing the carriage of oxygen in aeroplanes are in EASA publication EU OPS 1, subpart K. They require that pressurized aeroplanes carry oxygen for use in case of failure of the pressurization system, and that unpressurized aeroplanes have oxygen available if they are operated above 10,000 feet. All aeroplanes above a certain weight also require oxygen for use should the cabin air become contaminated. The regulations divide the oxygen requirements into 3 groups. These are supplemental oxygen, first aid oxygen, and protective breathing equipment oxygen. Oxygen is a non-flammable, heavier-than-air gas, which supports combustion as well as life. There are a number of general safety precautions that need to be taken with and around all oxygen systems. Specific precautions for individual aircraft types are contained in the appropriate aircraft manual, and you should familiarise yourself with the safety precautions for your aircraft type. Any flammable material will burn more fiercely in the presence of oxygen than in air. Smoking is therefore banned in oxygen-rich atmospheres, and all combustible materials should be removed from the area of oxygen recharging operations. Care should be taken to avoid causing sparks. No oil or grease should be allowed to come into contact with oxygen, as there is the possibility of a severe chemical reaction and spontaneous combustion. This means that tools, protective clothing and so on must be free from oil and grease. Any moisture present in the oxygen can cause corrosion, and there is the possibility of valves freezing as the oxygen flows through them. It is therefore essential that aircraft are replenished only with oxygen approved for aviation use. Aircraft quality oxygen has particularly low moisture content. Only lubricants specified in the maintenance manuals may be used. The permitted lubricants are normally graphite-based. Graphite grease is conductive, thereby reducing the risk of sparks, and it doesn't freeze. During replenishment or maintenance of oxygen systems, the surrounding area must be adequately ventilated. Remember that oxygen is heavier than air and will fill low-lying areas such as servicing pits. That is the end of the lesson. You should now have an understanding of the cause and effects of hypoxia. Hypoxia is covered in greater detail in the Human Performance series of lessons. You should know the precautions to be taken around oxygen equipment. In this lesson, we will examine the regulations governing the use of supplemental oxygen and the flight crew supplemental oxygen systems that are required by the regulations. Supplemental oxygen is oxygen which is used to allow the crew and passengers to breathe normally at altitudes where they would not otherwise be able to do so without the onset of hypoxia. For flight and cabin crews of pressurized aeroplanes, supplemental oxygen must be available for any time longer than 30 minutes that the cabin is between 10,000 and 13,000 feet, and for the entire time that the cabin is above 13,000 feet pressure altitude. The minimum amount of flight deck supplemental oxygen to be carried must be sufficient for at least 30 minutes use for aeroplanes certified to fly at altitudes not exceeding 25,000 feet, and for 2 hours for aeroplanes certified to fly above 25,000 feet. There must be sufficient supplemental oxygen carried on a pressurized aeroplane to supply all of the passengers on board with oxygen when the cabin is above 15,000 feet pressure altitude, with a minimum of 10 minutes supply available. There must also be sufficient oxygen available for 30% of the passengers when the cabin is above 14,000 feet and for 10% above 10,000 feet. For unpressurized aeroplanes, oxygen must be available for the flight crew at all times above 10,000 feet. For the cabin crew, oxygen must be available at all times above 13,000 feet. And at all times longer than 30 minutes above 10,000 feet. There must be sufficient supplemental oxygen available for all passengers on board when the aeroplane is above 13,000 feet. And for 10% of the passengers above 10,000 feet. Flight deck crew supplemental oxygen is stored in high-pressure gas cylinders. Oxygen is stored in the cylinders at a pressure of 1,800 pounds per square inch, with the pressure being reduced by a pressure regulator or pressure-reducing valve to a suitable level for use. Oxygen pressure indication is provided for the crew by a gauge on the flight deck. In the event of the pressure inside the cylinder becoming excessive, the cylinder is vented to atmosphere through a safety disc. Indication of this fact is given by a discharge indicator located on the outer skin of the aircraft. In the event of a discharge, the green disc will be ejected, leaving a red painted area visible. The cylinders are fitted with shut-off valves to enable them to be removed from the aircraft for maintenance purposes. There is a charging valve to allow the cylinders to be replenished in situ. On some systems, there is a system shut-off valve on the flight deck to allow the crew to shut off the supply if required in an emergency. Flight crew systems are generally of the diluter demand type, although on some smaller aircraft, the flight deck may have a continuous flow type of system. In the diluter demand type of system, the flow of oxygen to the flight crew masks is controlled by a diluter demand regulator. On some aircraft, the regulator is a separate component. On others, it is an integral part of the mask. The diagram on the screen is of a panel-mounted regulator. However, the operating principle is the same for an integral regulator. The diluter demand regulator supplies oxygen on demand. Depending on pilot selection, this can be oxygen diluted with cabin air, 100% oxygen, or 100% oxygen flowing continuously under a slight positive pressure. There are 3 pilot-controlled levers on the face of the regulator. There is a supply lever with on and off positions, an oxygen selection lever with normal and 100% positions, and an emergency lever with 3 positions marked normal, emergency, and test mask. In the emergency position, 100% oxygen under pressure will be supplied. The oxygen enters the regulator through the inlet. The first component it meets is the shut-off valve. This valve is controlled by the supply lever. With the lever to off, the valve is closed. The on position opens the shut-off valve and allows oxygen to flow into the regulator. The oxygen will now flow through the flow indicator to the demand valve. The flow indicator is a simple mechanical device, which will be blank when there is no flow and will be white or yellow when oxygen is flowing. The position of the demand valve is controlled by the demand diaphragm. The demand diaphragm is sensing cabin pressure on one face and oxygen mask suction on the other. If the mask is not being worn or the wearer is not inhaling, then the two pressures will be equal and the demand valve will be closed, blocking off the flow of oxygen. When the pilot breathes in through the mask, there will be a pressure reduction felt on the right side of the diaphragm, and the demand valve will open, allowing oxygen to flow through it to the air metering valve. The position of the air metering valve is controlled by the aneroid or evacuated capsule. The capsule is surrounded by cabin air. With the cabin at sea level, the capsule will be compressed, and the air metering valve will be fully to the right. In this position, a large amount of cabin air will enter the regulator through the air inlet non-return valve and mix with a small amount of oxygen before being fed to the mask. As the cabin altitude increases, the cabin pressure will fall. The capsule will therefore expand, moving the air metering valve to the left, allowing the ratio of oxygen to air to increase until, at a cabin altitude of 32,000 feet, the cabin air will be shut off and 100% oxygen will be supplied. If the cabin air is contaminated, possibly by smoke, to prevent the pilot breathing contaminated air, 100% oxygen can be selected using the oxygen selection lever. Moving the lever to the 100% position closes off the cabin air inlet and opens the supplementary oxygen valve, bypassing the air metering valve, allowing the pilot to breathe pure oxygen. In the event of thick smoke, high cabin altitude or stress, pilots can select 100% oxygen with a positive pressure using the emergency lever. When emergency is selected, the demand diaphragm is pushed to the right, unseating the demand valve, allowing a constant flow of oxygen at a pressure higher than the cabin pressure to enter the mask. This gives a positive pressure within the face mask, which ensures that smoke is kept out and increases the oxygen saturation of the pilot's blood. The emergency lever also has a spring-loaded test mask position. This position opens the demand valve and allows oxygen at a high pressure to flow to the mask. The relief valve will bleed off oxygen should the pressure in the regulator become excessive, possibly due to failure of the pressure regulator. It is a regulatory requirement that quick donning masks be provided for the flight deck crew on all aircraft that have a maximum operating altitude above 25,000 feet. The mask must be capable of being fitted with one hand in a maximum time of 5 seconds. The pilot must be able to carry out all normal communication tasks with the mask fitted. A typical example of a quick donning mask is shown here. It is a combined mask and regulator. The regulator has all the features of the panel-mounted regulator. When not required for use, the mask is stowed in a panel-mounted box, in such a way that the regulator controls and the feed hose protrude through apertures in the stowage doors. When the mask regulator is stowed and the box doors closed, oxygen flow to the mask is prevented by a shut-off valve inside the box, this valve being held closed by the reset test lever on the left door. The flow indicator is visible with the doors open or closed. The mask is held to the face by a harness constructed of elastic tubes. The tubes are inflated by oxygen to allow rapid donning of the mask. The harness is deflated when stowed. It will fit all head sizes. The control for normal or 100% oxygen flow is a lever on the front of the mask, marked N, and 100% push. The N position is equivalent to the normal position on the panel-mounted regulator and will give an oxygen-air mixture on demand. By pushing the lever to the 100% push position, the wearer will receive 100% oxygen on demand. Rotating the emergency control knob to the emergency position changes the flow from diluter demand to a positive flow, in the same manner as the emergency lever on the panel regulator. The emergency knob is also marked Press to Test. This allows the mask to be tested while stowed. When pressed together with the Reset Test lever, it allows oxygen to flow into the mask. Flow is checked on the flow indicator. The mask is withdrawn by grasping the red release grips between thumb and forefinger. This action causes oxygen to inflate the harness, allowing the mask to be rapidly fitted to the face. Subsequent release of the grips deflates the harness, which will now form-fit the head. The masks have microphones connected to the aircraft's communication systems. Some have integral smoke goggles, as shown here. On others, there is a mask ventilation feature, which, when selected, will provide ventilation to the separate smoke goggles, which sit over the nose section of the mask in order to overcome misting problems. The vent valve selector is slid down to open the vent valve and allow oxygen into the goggles. That is the end of the lesson on flight crew supplemental oxygen. A summary of the regulatory requirements is shown on the screen. The full regulations can be downloaded from the JAA website. Remember that the regulations about the amount of passenger oxygen to be carried appertain to the actual number of passengers on board. The regulations need to be memorized. Click to continue with the lesson summary when you are ready. Here is a summary of the other main points of the lesson. Flight deck crew supplemental oxygen is stored in high-pressure gas cylinders. Flight crew masks for aeroplanes operating above 25,000 feet must be of the quick donning type. The mask must be capable of being fitted with one hand in a maximum time of 5 seconds. The pilot must be able to carry out normal communication tasks with the mask fitted. Each flight crew member has a diluter demand type of oxygen regulator. The graphic on the screen summarizes the operation of the diluter demand regulator. In this lesson, we will examine the supplemental oxygen systems provided for passengers and cabin crew. The regulations governing the use of supplemental oxygen throughout the aeroplane are covered in the flight deck supplemental oxygen lesson. The supply of supplemental oxygen to the passengers and cabin attendants is of the continuous flow type. That is to say that once the flow to a mask is initiated, it will continue whether someone is breathing the oxygen or not. On some smaller aircraft, the flight deck also has a continuous flow type of system. The cabin crew and passengers can be supplied by either a high-pressure gaseous system or a chemical generator system. The oxygen masks for the cabin crew and passengers are stowed in the passenger service units above the passengers' heads. This picture is looking down on the top of a typical passenger service unit. The doors of the units are opened automatically by a barometrically controlled release mechanism if the cabin altitude reaches 14,000 feet, or by manual selection by the flight crew at any altitude. There are two methods of automatic door actuation in use. In the gaseous system, they are opened pneumatically by the oxygen pressure. But if the system uses chemical generators, the doors are opened by electrical solenoids. When the passenger service unit doors open, the masks drop to the half-hung position. That is to say, they are now hanging by their initiation cords. Pulling the mask towards the face pulls the cord, which initiates the oxygen flow by opening a check valve in the gas supply system or operating the electrical or percussion cap firing mechanism on the chemical generator. The regulations require that for aeroplanes intended to be operated above 25,000 feet, the number of masks must exceed the number of cabin seats available by 10%, with the extra masks spread evenly throughout the cabin. This allows passengers and cabin crew not in their seating positions to quickly find a spare mask. In the picture shown, there are only 3 seats below the passenger service unit, but there are 4 masks stowed in the unit. The oxygen enters the mask through a plastic rebreather bag, where it is mixed with exhaled air and cabin air. Because of this mixing with cabin air, passenger oxygen masks don't give protection from noxious fumes. A passenger high-pressure gaseous oxygen supply system is very similar in design to the crew system, except that the demand regulators are replaced by mask connection points, with valves operated by the mask cords. There is also a flow control valve in the system, which can be opened automatically by a barometric switch when the cabin altitude exceeds 14,000 feet, or manually by operation of a flight deck switch. Chemical oxygen generators, which are used on most modern aircraft, are relatively light and inexpensive self-contained devices, which require virtually no maintenance. In a system using chemical oxygen generation, the generators are located in each passenger, cabin crew and lavatory service unit. Each generator can supply 2, 3 or 4 passenger oxygen masks. Here is a cross-section of a typical aviation chemical oxygen generator. Inside a cylindrical case is a charge block made up of a mixture of sodium chlorate and iron powder. This is surrounded by a filter material and thermal insulation. In the older chemical oxygen generator units, as the mask is pulled down, a cord attached to the mask operates a percussion cap in the firing mechanism, igniting the charge block. In more modern systems, when the mask is pulled down, the cord operates an electrical switch, which fires a 28-volt DC squib to begin the ignition process. When ignited, the charge block will burn at a temperature of approximately 200 degrees Celsius and will burn for a minimum of 15 minutes, releasing about 45% of its weight as usable oxygen through the oxygen outlets. The sodium chlorate and iron core is shaped to provide maximum oxygen flow initially. This will be when the cabin altitude is highest and the maximum oxygen is required. This table shows the relationship between the amount of passenger oxygen required in an emergency descent compared to the capacity of a typical oxygen generator. You can see that the oxygen output is always slightly greater than the amount required. A filter in the generator removes any contaminants and cools the oxygen to a temperature not exceeding 10 degrees Celsius above cabin ambient temperature. A relief valve prevents the internal pressure in the generator exceeding 50 psi. The normal flow pressure is 10 psi. Chemical oxygen generators need to be treated with caution. The chemical reaction generates a lot of heat. The case of the generator becomes very hot. Once the chemical reaction has started, it cannot be stopped. A strip of heat-sensitive tape or paint on the case changes colour, in this case from orange to black, when the generator is used, and provides a visual indication that the generator needs to be replaced. That is the end of the lesson. Here is a summary of the main points. Cabin crew and passenger supplemental oxygen systems can be gaseous, or they may use chemical oxygen generators. Chemical oxygen generators are usually used because they are inexpensive, light, and are almost maintenance-free. In the event of a depressurization, when the cabin altitude exceeds 14,000 feet, oxygen masks will automatically be presented to the cabin crew and passengers. The passenger oxygen masks can be deployed at any time by operation of a switch on the flight deck. The flow of oxygen to a mask is normally initiated by pulling the mask towards the face. A mixture of oxygen and cabin air is breathed in through a passenger mask. In this lesson, we will examine the regulations pertaining to the carriage of first aid oxygen, and we will look at the equipment fitted to aeroplanes to comply with these regulations. First aid oxygen is for use by passengers who may require oxygen following a depressurization, even though the aeroplane has descended to a pressure altitude where normal breathing should be possible. This oxygen is not carried for use by passengers with pathological respiratory problems. For such passengers, extra oxygen must be carried. All pressurized aeroplanes which operate above 25,000 feet and which carry a cabin crew member must have first aid oxygen available. There must be sufficient first aid oxygen to supply 2% of the actual number of passengers carried for the remainder of a flight, following cabin pressurization failure, while the cabin altitude is between 8,000 and 15,000 feet. The first aid oxygen equipment must be capable of generating a flow rate of 4 litres per minute to each user. However, the equipment may have a means of reducing the flow rate to not less than 2 litres per minute. First aid oxygen is normally stored in portable cylinders. The cylinders are installed at suitable locations in the passenger cabin. Masks are stowed adjacent to the cylinders. The cylinders normally contain 120 litres of oxygen at a pressure of 1800 psi and are fitted with a carrying strap. A regulator is fitted to the top of the cylinder. It has an on-off control knob, a pressure gauge, and in our examples shown here, 2 outlets marked high and low. The high outlet provides 4 litres of oxygen per minute to the user, and low 2 litres per minute. At a rate of 2 litres of oxygen per minute, a 120-litre cylinder would last 60 minutes. This reduces to 30 minutes at 4 litres per minute. Larger cylinders with more than one outlet for multiple supplies are also sometimes used. Remember that first aid oxygen is for use by passengers who may require oxygen following a depressurization. It is not carried for use by passengers with pathological respiratory problems. The only other important points to be taken from this lesson are the regulations about first aid oxygen, which must be memorized. They are summarized on the screen. The EASA regulations stipulate that protective breathing equipment, known as PBE, be available for all crew members. In this lesson, we will look at the equipment used to comply with this regulation. For the flight crew, the requirement can be met from the flight crew supplemental oxygen system. However, this is not portable, and additional portable PBE is often available on the flight deck. Each cabin crew member must have portable PBE available for their use. The regulations state that a portable PBE unit must also be available adjacent to each required hand fire extinguisher. Protective breathing equipment must be able to protect the eyes, nose and mouth of the wearer, and provide breathing gas for a minimum period of 15 minutes. This protection can be provided using a first aid oxygen bottle with a full face mask. But more often it is provided by smoke hoods, a typical example of which is the Draeger Oxcrew hood. However, there are a number of different types of hood in use, and you should familiarize yourself with the hoods being used on your aircraft. The smoke hood is stored in a vacuum package inside a lightweight, rigid container. An installation bracket allows the container to be fixed at an appropriate location on board the aircraft. The donning instructions are shown on the case. The smoke hood consists of a heat-protecting hood and a mask, with an integrated speech transmitter. The chest bag part of the hood contains a small chemical oxygen generator and a breathing bag connected to a cartridge which absorbs carbon dioxide and humidity and produces oxygen. This forms a closed-loop breathing system. Once the hood is on the head, a tag on the bottom of the chest bag is pulled to initiate the oxygen production process. In this lesson, we will discuss the fire detection systems fitted to all aircraft. A fire cannot exist without three things being present. These are heat, or a source of ignition, fuel, material that will burn, and oxygen. This is known as the triangle of fire. Take any one of the three away and the fire will go out. A fire in an aircraft is extremely dangerous. So to protect the aircraft, the crew and the passengers, aircraft must have fire detection and extinguishing systems fitted in all areas where a potential fire risk may exist, following failure of or leakage from any component or associated equipment. The specific areas that require protection are the engines, the auxiliary power unit or APU, the main wheel wells, and the cargo compartments. These areas are known as designated fire zones, and they must have detection systems fitted to warn the crew of a fire. In the case of the engines and the auxiliary power unit, they are isolated by fireproof bulkheads known as firewalls, normally manufactured from titanium or stainless steel, which will contain any fire to the immediate area and prevent it from spreading to the rest of the aircraft. Each designated fire zone must have a fire detection system which is capable of providing rapid detection and warning of a localized fire or overheat condition. There are a number of detection systems in use, and we will now take a look at them. Differential expansion detectors use the fact that when heat is applied to different materials, they will expand at different rates. A detector consists of a pair of contacts mounted on a spring bow assembly, fitted within an expansion tube, which is mounted on a base. The spring bow is fixed to the tube at the top and the bottom. When heat is applied, the tube expands at a greater rate than the bow, drawing the contacts together. When the contacts come together, they provide power to the warning circuit. A subsequent drop in temperature will cause the tube to shorten, the contact to open, and the warning to stop. This type of detector usually incorporates a short time delay before the warning is activated, to prevent false warnings due to vibration. Differential expansion detectors are often used to monitor engine cooling air outlets in order to provide internal engine overheat warning. In the event of this warning being given, the pilots will normally be required to shut down the engine. Engine and auxiliary power unit fire zones are often fitted with continuous loop fire detectors, commonly known as fire-wire systems. A detector unit consists of a stainless steel tube with a central electrode insulated from the tube by a core of temperature-sensitive material. Firewire detectors operate on the principle of their core material having either a negative coefficient of resistance with temperature or a positive coefficient of capacitance with temperature. In one system, both methods are used together. In the resistive type of firewire, as the temperature increases, the resistance of the insulating material decreases. This causes the current flow between the central electrode and the outer tube to increase, until, at a predetermined temperature, sufficient current will flow and the warning system will operate. If the temperature drops back below a preset value, the system will automatically reset, and the warning will stop. This type of detector will react and give a fire warning if there is an isolated temperature increase, for instance, from a direct flame, or if the temperature of the entire detector increases, possibly because of a hot gas leak. Because the loop is connected to the control unit at both ends, the system will continue functioning with a single break in the firewire. One particular problem with this type of system is that a short circuit between the case and the inner electrode will give a false fire warning. In the capacitive type of system, the detector acts as a long capacitor, with the core material acting as the dielectric, and the case and the inner electrode as the poles. The case and the inner electrode are connected across an AC supply. An increase in temperature causes a change in the properties of the inner core material. This change increases the capacitance of the detector. The firewire is polarized by the application of half-wave rectified alternating current from a control unit, which it stores and then discharges as a feedback current. As the capacitance increases with temperature increase, so will the feedback current. Once the feedback current reaches a predetermined level, it activates the fire warning. As with the resistive type, this system will reset itself once the temperature drops below a preset level. This type of detector will also react and give a fire warning if there is an isolated temperature increase, for instance from a direct flame, or if the temperature of the entire detector increases. Again, as with the resistive system, the loop is connected to the control unit at both ends. So the system will continue to operate normally in the event of a single break in the firewire. This system has the advantage over the resistive type in that a short-circuit grounding of the element or system will cause the capacitance to fall to zero, so will not result in a false warning. Firewires are positioned around engine fire zones in a continuous double loop. The two loops are normally known as Loop A and Loop B. The two loops operate independently. Both loops need to detect a fire to initiate the warning. In this way, spurious warnings caused by one loop giving a false fire indication, possibly due to a short circuit, are prevented. Warning of any loop failure may be displayed on the fire detection panel or electronic system display unit. The last system we are going to look at is the gas-filled detector system. This system consists of a number of sensing elements which look very similar to firewire, and they are used in a very similar way. The tube has a central core, made up of a material which will give off hydrogen gas when heated to a high temperature. During the manufacturing process, helium gas is forced into the tube under pressure. The tube is then sealed. To aid explanation of the gas-filled detector type of system, we have included a pressure gauge. This gauge is not fitted on aircraft detection systems. The pressure in the tube is monitored by two pressure switches. One is closed at the tube's normal pressure. This is known as the integrity switch. The other, which is open at normal pressure, is known as the alarm switch. As with firewire, the detectors are positioned around the fire zones in a double loop, with both loops again being required to detect a fire before a fire warning is given. When the gas-filled detector tube is heated locally by a flame, the helium pressure may not increase sufficiently to trigger the warning. However, hydrogen gas is released from the core material, and the pressure in the tube will build up. This increase of pressure is sensed by the alarm pressure switch, which will close. This will send a signal to a control box, which will initiate a fire warning. In the event of a hot gas leak, the temperature increase will be less than that caused by a flame, but it will be felt over a larger area of the detector. This increase in temperature may be insufficient to cause the release of hydrogen gas, but it will cause sufficient increase in the pressure of the helium gas to close the alarm pressure switch and initiate a fire warning. Should the tube be damaged, and the helium gas be released from the core, the pressure will fall and the normally closed integrity pressure switch will open. This will cause a fault indication on the control panel or electronic systems display. Whichever detection system is used, flight deck indications of an engine fire will normally be both aural and visual. The aural warning will normally be a bell or a klaxon, or possibly a continuous repetitive chime. Visually, there may be a master fire warning caption and a steady red fire warning light for each engine. Before flight, a means must be available to test the fire warning circuit. A fire test selector is therefore provided for the flight crew. With differential expansion detectors, a simple continuity test is carried out on the wiring between the detector or detectors and the warning light. A satisfactory test is indicated by illumination of the warning light. When a fire test is initiated on a fire wire system, a continuity test is carried out on both the outer tube and the inner electrode. A satisfactory test is indicated by a full fire warning being displayed for all engines being tested. Should there be a break in either the tube or the electrode of the fire wire for a particular engine, then the test will fail, and a fire warning will not be given for that engine. When a fire test is carried out on the gas-filled system, again the integrity of the loops is tested. But also, if the gas has leaked out and the integrity switch is open, then the test will fail. In some fire wire and gas-filled detector systems, a warning is given to notify crews if a single fire loop should fail in flight. The system may now automatically switch to single loop operation, with a fire warning being given if the serviceable loop alone senses a fire. Depending on aircraft type, a limited number of sectors may be permitted to be flown in the single loop mode. That is the end of the lesson. Here is a summary of the main points. Click to go on to the next one once you are sure you understand the point being displayed. The areas of an aircraft fitted with fire protection systems are the engines, the auxiliary power unit, the main wheel bays, and the cargo compartments. Differential expansion fire detectors use the fact that when heat is applied to different materials, they will expand at different rates. Remember that these detectors usually have a time delay built into their warning circuits to prevent false alarms caused by vibration. Resistance and capacitive firewire systems have the detector connected at both ends. So with a single break, the detector will continue to function. The system test checks the continuity of the loop as well as the warning system, so if there is a break, the test will fail. If a resistive firewire is short-circuited, it will give a fire warning. The gas-filled system uses the fact that the pressure of the gas in the detector increases with increasing temperature to trigger a fire warning. When a test is carried out on the gas-filled system, the integrity of the loops is tested. If the gas has leaked out, the integrity switch will open and the test will fail. Finally, flight deck indications of an engine fire will normally be both aural and visual. In this lesson, we will examine the fixed engine fire extinguishing systems that are used on aircraft. The designated fire zones for the engines and the auxiliary power unit, or APU, have fixed fire extinguishing systems fitted. The cargo or baggage compartments and wheel wells may also have fixed systems. In the event of a fire extinguishant can be sprayed into the fire zone by a fixed fire extinguisher or extinguishers. A fixed fire extinguishing system normally comprises fire bottles, filled with a fire extinguishing agent under pressure, connected via piping to the fire zones. It is an EASA regulatory requirement that a single discharge, or shot, will provide an agent concentration capable of extinguishing a fire in that zone and of minimizing the probability of reignition. For aeroplane engines, 2 discharges or shots must be provided, each of which produces adequate agent concentration to extinguish an engine fire. This requirement may be covered by having 2 fire bottles per engine, or in some systems by having 2 bottles, both of which can be discharged into either one of 2 engines. A means of discharging the fire bottle is provided on the flight deck. The discharge system is only armed after the fire switch has been operated to shut down the engine and shut off any flammable fluid. In this example, the squib lights come on in the extinguisher push buttons when the fire switch is operated, to indicate that the buttons are now armed. There is an electrically operated explosive cartridge, known as a squib, situated between the base of the fire bottle and the piping. Operating the fire extinguisher button fires the cartridge, allowing fire extinguishant, under pressure, to enter the engine nacelle fire zone. The subsequent reduction in bottle pressure operates a low-pressure electrical switch, which illuminates the discharge caption in the bottle selector. Each fire bottle may have a bottle pressure gauge. However, this may not be visible externally, and panel access may be required. If the pressure inside a fire bottle becomes excessive, due to it being exposed to a high temperature, its contents will be discharged overboard through a thermal discharge port, before the pressure becomes such that the bottle explodes. In this circumstance, the bottle pressure gauge will read 0. On some aircraft, where the bottle pressure gauges are not readily visible to the crew on an external inspection, indicator discs connected to the thermal discharge pipes are fitted externally in a position where they are easily visible. These may take the form of a green disc, which will be ejected by the thermal discharge pressure, allowing a red disc below it to show, or a red disc, the absence of which indicates a thermal discharge. On aircraft with a pressure-operated flight deck discharge light, this will be illuminated. All aircraft will have an engine fire checklist, which must be carried out in the event of an engine fire. It is important that this checklist is carried out in a controlled manner, and that all actions are completed in the correct order. A typical engine fire checklist will contain the following items. The first step will usually be to cancel the aural warning. On some aircraft, the aural warning can be silenced by pressing a bell cancel button. On others, operating the fire switch silences the aural warning. The next step will be to shut off the fuel to the engine. This is done by closing the engine high-pressure fuel valve. In the typical system shown here, closing the engine master switch performs this function. Next, bleed air, electrics, hydraulics, and engine de-icing are shut off. On modern aircraft, all of these actions are usually achieved by operating a fire switch or handle. Operation of the switch will also close the low-pressure fuel valve. Operation of the fire switch will also arm the fire extinguisher discharge switches. The first fire bottle is then discharged into the engine fire zones. If the fire has not gone out after a specified period of time, the second fire bottle is discharged. Bear in mind that this is only a generalization, and it is important that you carry out the engine fire checklist for your particular aircraft exactly as it is laid down. That is the end of the lesson. In this lesson, you have learned that each engine must have 2 fire extinguishers, each of which is capable of extinguishing an engine fire. This can be achieved by having 2 fire bottles per engine, or by having 2 fire bottles shared by 2 engines, with both bottles being able to be discharged into either engine. You have seen that when an engine fire handle is pulled, or the fire switch is pushed, it will shut off electrics, hydraulics and bleed air, and close the low pressure valve in the engine fuel system. It will also arm the fire extinguishing system. In this lesson, we will look at the various fire extinguishing agents available for use in and on aircraft. We will also discuss the regulations governing both the number and the types of handheld fire extinguishers required on an aeroplane. The type and quantity of extinguishing agent must be suitable for the kinds of fires likely to occur in the compartment where the extinguisher is intended to be used. And for personnel compartments, the hazard of toxic gas concentration must be minimal. Bromochlorodifluoromethane, BCF, is the most commonly used agent. It is also known as Halon 1211. It is stored in signal red, purple, brown, or green containers. This agent is very effective against electrical and flammable liquid fires. It is only slightly toxic. It is colourless, non-corrosive, and evaporates rapidly, leaving no residue. It does not freeze or cause coal burns, and will not harm fabrics, metals, or other materials it comes into contact with. It acts rapidly on fires by producing a heavy blanketing mist, which eliminates air from the fire source, but more importantly, it interferes chemically with the combustion process. It has outstanding properties in preventing reignition after the fire has been extinguished. Along with Halon 1301, it is widely used in the fixed fire extinguishers fitted to gas turbine engine power plants and in cargo compartments. It has the advantage that it can be directed as a liquid stream from a handheld fire extinguisher, allowing the user to fight fires from a safe distance. Many of the handheld fire extinguishers in crew and passenger compartments are BCF. Bromotrifluoromethane, BTM, or Halon 1301, is stored in grey containers and used in fixed systems for the protection of auxiliary power units, power plants and cargo compartments. It has similar characteristics to Halon 1211, except that it has a vapour spray which is more difficult to direct. For this reason, it is not normally found in handheld fire extinguishers. BCF and BTM are part of a group of halogenated hydrocarbons, commonly called Freon. There are other extinguishing agents in the Freon group, but only BCF and BTM extinguishers are recommended for use on aircraft. Water, or water glycol, is stored in red or grey containers and is used in handheld portable appliances. The only purpose of the glycol is to stop the water freezing at low temperatures. It can be used in passenger cabins for combating fires involving domestic materials. It must not be used on fires which involve electrical equipment or liquids, nor should it be applied to hot breaks. The glycol is an antifreeze agent, which permits operation of the extinguishers at temperatures as low as -20 degrees Celsius. Dry chemical or dry powder extinguishant is stored in a blue or red container with a blue label. The use of this agent in crew compartments or any other compartment not separated by a partition from the flight deck of large aircraft is not permitted. However, some light aircraft may carry dry powder extinguishers, and their use should be avoided if at all possible, as visibility will be restricted and the powder can render otherwise serviceable electrical equipment inoperative. The agent is a non-toxic powder, usually potassium bicarbonate, which is similar to talcum powder. It is very effective against fires involving liquids, wood, fabric and paper. It should not be used on electrical fires, as it will cause damage to any otherwise serviceable electrical equipment. Dry powder is best known for its application against wheel and brake fires on the ground. As a powder, it has no cooling effect, and this reduces the danger of wheel explosions or the distortion of the brakes and wheels. In addition to the dry powder extinguisher, foam, water, carbon dioxide, BCF and sand are available for use by personnel on the ground for extinguishing aircraft fires. Carbon dioxide is stored in black or red containers with a black label. It is non-corrosive and extinguishes fire by dissipating the oxygen in the immediate area. From a standpoint of toxicity and corrosion, it is the safest agent to use, and for many years it was the most widely used. If handled improperly, it can cause mental confusion and suffocation. For this reason, the EASA regulations state that no more than 5 pounds of carbon dioxide may be discharged into any fuselage compartment, so it is not normally used inside aircraft. Carbon dioxide may be used against most types of fire, and is particularly useful against engine fires, as it will extinguish the fire without damaging the engine. This agent may be used as a substitute for dry powder against wheel and brake fires. However, it should not be sprayed directly onto the wheel, but alongside, to blanket the wheel with a carbon dioxide cloud. Foam is the principal extinguishant for use on flammable liquid fires, including liquid butane and propane. It blankets the flames by excluding oxygen. Sand is useful for containing metal fires, such as those involving magnesium or titanium, where liquids will make matters worse. The EASA regulations state that the number of handheld fire extinguishers required in the passenger compartment will be governed by the maximum approved passenger seating configuration in the compartment. The table on the screen shows the requirements. They need to be memorized. There are two things worth remembering about this table. Firstly, the requirement relates to the maximum approved passenger seating configuration, not the number of passengers being carried. So, for instance, an aircraft with a maximum approved passenger configuration of 200 must have 3 fire extinguishers in the passenger compartment, even if there are only 50 passengers on board. Secondly, this requirement does not include handheld fire extinguishers that may be required in other compartments. At least one of the required fire extinguishers, located in the passenger compartment of an aeroplane with a maximum approved passenger seating configuration of at least 31 and not more than 60, and at least 2 of the fire extinguishers located in the passenger compartment of an aeroplane with a maximum approved passenger seating configuration of 61 or more, must contain BCF or an approved equivalent as the extinguishing agent. In addition to these requirements, there must also be at least one BCF hand extinguisher conveniently located on the flight deck for use by the flight crew. To make sure you understand, try this. If an aeroplane has a maximum approved passenger seating configuration of 201, but is only carrying 200 passengers, how many handheld fire extinguishers must be on the aeroplane? And how many of them must be BCF? Well done! Just to confirm it, here is the table which shows we need 4 handheld extinguishers for the passenger compartment, 2 of which must be BCF, plus 1 BCF for the flight deck. In this lesson, you have learned that there are various extinguishers available for different types of fire. Bear in mind that you need to memorize the table of handheld fire extinguisher requirements. In this lesson, we will describe the locations in an aeroplane where smoke detection systems are likely to be used. Then we will go on to describe the various smoke detection systems in use, including the types of warning they give and how they can be tested. The areas on aeroplanes usually fitted with smoke detection systems are the cargo and baggage compartments, electrical equipment bays, and toilets. Smoke detection sensors operate on one of 2 principles. They are either optical, using light sensors, or ionizing, utilizing a small amount of radioactive material. The optical type of smoke detector contains a light source, the projector lamp, and a photoelectric cell. A photoelectric cell is a device which produces electricity when it is exposed to light. The greater the level of light, the greater the electrical current it will produce. The photoelectric cell is sitting in darkness. It is shielded from the light source's output by an opaque barrier. Outside light is prevented from entering by the light-tight louvers, but air can flow freely through the unit. If smoke enters the unit, it will scatter the light. This will cause some light to be seen by the photoelectric cell. The cell will now produce an output which will trigger an alarm. There is a test lamp in the unit. This lamp is positioned so that when it is switched on, some of its light will be seen by the photoelectric cell, generating a smoke warning. Ionization smoke detectors use an ionization chamber and a source of ionizing radiation to detect smoke. The ionization chamber consists of two plates with a voltage across them, along with a radioactive source of ionizing radiation. The alpha particles generated by the radioactive material ionize the oxygen and nitrogen atoms of the air in the chamber. To ionize means to remove an electron from. When you remove an electron from an atom, you end up with a free electron with a negative charge and an atom missing one electron with a positive charge. The negative electron is attracted to the plate with a positive voltage, and the positive atom, which is known as an ion, is attracted to the plate with a negative voltage. Opposites attract, just like with magnets. The control circuit senses the small amount of electrical current that these electrons and ions moving towards the plates represent. When smoke enters the ionization chamber, it disrupts this current. The smoke particles attach to the ions and neutralize them. The smoke detector control circuit senses the drop in current between the plates and produces a warning. The two types of detector, optical and ionization, both have advantages and disadvantages. The optical detector is very good at detecting low-heat, smouldering types of fire with lots of visible smoke. However, it is not very efficient at detecting high-heat fires, where the smoke particles are much smaller. The ionization type of detector has the opposite properties. It is very slow to detect smouldering fires, but quickly detects the smoke produced by high-heat fires. Smoke detectors of all types can give false alarms if they are exposed to dust or dirt, or even the fumes from certain types of fruit being carried in the cargo compartment. Durians being a prime example. Ionization smoke detectors are commonly found in domestic units and aircraft toilets. Most aircraft smoke detectors, with the exception of those used in toilets, are of the optical type. One of the primary uses for optical smoke detectors is in cargo compartment smoke detection systems. Cargo compartment smoke detectors are usually fitted in pairs to help prevent spurious warnings, both detectors needing to sense smoke before a warning is given. If the compartment is large, a number of pairs of detectors may be used. A typical cargo compartment and smoke warning panel is shown here. We will go through the sequence of events which will occur in the case of an aft cargo smoke warning. If a pair of aft cargo detectors sense smoke, the red smoke light will come on. At the same time, the fire bell or chime will sound. The pilot will cancel the aural warning, then carry out the cargo fire warning checklist. In the particular system shown here, there are 2 cargo fire bottles. The pilot will raise the guard and operate the discharge switch to discharge cargo fire bottle 1 into the compartment. Operating this switch will also close off all ventilation into the compartment. When the bottle discharges, the discharge light will illuminate. If, after a preset period of time, the fire has not gone out, the discharge agent 2 light will illuminate. This is the cue for the pilot to once again raise the guard and discharge the second fire bottle into the compartment. It is a regulatory requirement that on aeroplanes with a passenger capacity of 20 or more, each lavatory must be equipped with a smoke detector system, or an approved equivalent, that provides a warning light in the cockpit, or provides a warning light or audible warning in the passenger cabin that will be readily detected by a cabin crew member. If smoke is detected in a lavatory, a warning light will come on outside the affected lavatory. The cabin chimes will sound, and a warning will be given both orally and visually at the senior cabin crew member station. The aural warning can be cancelled, but the warning light will remain lit until the smoke has cleared and the reset button is pressed. That is the end of the lesson. Here is a summary of the main points. Smoke detectors may be fitted in cargo and baggage compartments, electrical equipment bays, and toilets. Smoke detection sensors operate on one of 2 principles. They are either optical, using light sensors, or ionizing, utilizing a small amount of radioactive material. Cargo compartment smoke detectors are usually fitted in pairs to help prevent spurious warnings, both detectors needing to sense smoke before a warning is given. It is a regulatory requirement that on aeroplanes with a passenger capacity of 20 or more, each lavatory must be equipped with a smoke detector system or equivalent that provides a warning light in the cockpit, or provides a warning light or audible warning in the passenger cabin that will be readily detected by a cabin crew member. Auxiliary power units, APUs, are constant speed self-contained gas turbine engines, which derive their fuel supply from the aircraft system. They may be used to supply bleed air and hydraulic and electrical power to the aircraft systems on the ground, prior to main engine start. They can, if certified, be available for airborne use in an emergency. It is permissible to run the auxiliary power unit unmonitored, and for this reason there is a self-monitoring system which will automatically shut it down in the case of a major failure, including fire. On some types, the auto-shutdown system only operates when the aircraft is on the ground. The APU fire detection system uses the same type of dual-loop detectors as the main engines. In most installations, there is only one fire extinguisher bottle. In some installations, the fire extinguisher will automatically discharge in the event of a fire. In others, the pilot needs to operate the discharge switch. There may be an external auxiliary power unit control panel, which will include a fire warning horn and a means of shutting down the APU. This panel is for use by personnel working on the outside of the aircraft. It is a certification requirement that all aeroplanes with a passenger carrying capacity of 20 or more must have an automatic fire extinguisher built into each disposal receptacle for towels, paper or waste located within a lavatory. Each lavatory must also have a smoke detector fitted to warn the crew of smoke in the lavatory. Smoke detectors are covered in another lesson. The fire extinguishing system consists of a fire extinguisher located in the waste compartment. Its outlets are sealed with fusible plugs. At a preset temperature, the plugs will melt, allowing the extinguisher to fill the waste compartment with an inert gas, smothering the fire. There are two main points in this lesson. An auxiliary power unit may be unmonitored, and for this reason there is a self-monitoring system, which will automatically shut it down in the case of a major failure, including fire. In some installations, the fire extinguisher will automatically discharge in the event of a fire. It is a certification requirement that all aeroplanes with a passenger carrying capacity of 20 or more must have an automatic fire extinguisher built into each disposal receptacle for towels, paper or waste located within a lavatory. For fire protection purposes, the regulations split cargo and baggage compartments not occupied by crew or passengers into 5 classes, classes A through to E. There are different regulations for each class of compartment. A Class A compartment is one in which the presence of a fire would be easily discovered by a crew member whilst at his station, and for which each part of the compartment is easily accessible in flight. Typically, a Class A compartment is a small open compartment in the cockpit used for the storage of crew luggage. A Class B cargo or baggage compartment is one in which there is sufficient access in flight to enable a crew member to effectively reach any part of the compartment with the contents of a handheld fire extinguisher. It must be demonstrated in a test that when the access provisions are being used, no hazardous quantity of smoke, flames or extinguishing agent will enter any compartment occupied by the crew or passengers. The compartment must have a separate approved smoke detector or fire detector system to give warning to the pilot or flight engineer station. These compartments are often found on combi types of aircraft, where passengers are seated on the same deck as freight. A Class C cargo or baggage compartment is one not meeting the requirements for either a Class A or B compartment. It must have a separate approved smoke detector or fire detector system to give warning at the pilot or flight engineer station. There must be an approved built-in fire extinguishing or suppression system controllable from the cockpit. There must be means to exclude hazardous quantities of smoke, flames, or extinguishing agent from any compartment occupied by the crew or passengers. And there must be means to control ventilation and drafts within the compartment, so that the extinguishing agent used can control any fire that may start within the compartment. Most passenger aircraft underfloor baggage and freight compartments are Class C. Class D compartments are no longer permitted. A Class E cargo compartment is one on aeroplanes used only for the carriage of cargo. The compartment must have a separate approved smoke or fire detector system to give warning at the pilot or flight engineer's station. There must be a means to shut off the ventilating airflow to or within the compartment, and the controls for these means must be accessible to the flight crew in the crew compartment. There must be means to exclude hazardous quantities of smoke, flames or noxious gases from the flight crew compartment, and the required crew emergency exits must be accessible under any cargo loading condition. Class E compartments do not require fire extinguishing systems. Here is a table listing the regulations for the 5 classes of cargo compartment.
In this lesson, we will examine the properties of the various fuels used in aircraft engines. Aircraft piston engines use gasoline, and gas turbine engines kerosene. Both of these fuels are produced from crude oil. In simple terms, the required fuel is extracted from the crude oil by a distillation process. The oil is boiled in a furnace, and then the oil vapor is cooled in a distillation column. The various hydrocarbons in the oil all have different boiling points, so they condense out of the vapor and are tapped off at different points in the column. The heavy oils condense out first and are collected near the bottom. The process then continues up through the tower, with kerosene and gasoline, which are relatively light and volatile, being taken out near the top. The specification for an ideal fuel for either a gas turbine engine or a piston engine include the following main requirements. It should flow easily under all operating conditions. It should have complete combustion under all conditions. It needs to have a high calorific value. The calorific value is a measure of the amount of heat released during its combustion. It is measured in British thermal units per pound or kilojoules per kilogram. It should be non-corrosive. There should be no damage to the engine from combustion byproducts. The fuel should present a low fire hazard. Engines should start easily, and the fuel must be able to lubricate the moving parts of the fuel pumps and other components in the system. In practice, the cost of satisfying all these criteria is prohibitive, and therefore compromises have to be made. Piston-engined aircraft use gasoline fuels grouped under the title Aviation Gasoline or avgas. Aviation gasoline is manufactured to conform with the exacting specifications that are issued in the United Kingdom by the UK Aviation Fuels Committee on behalf of the Defence Material Standardisation Committee. The specification number for gasoline is Defence Standard, or DEFSTAN 91-90. Aviation gasoline is graded by octane rating. The octane rating of a fuel is a measure of the fuel's resistance to detonation when subjected to high temperature and pressure. A fuel's octane rating is checked in a test engine with the fuel-air mixture weak and with it rich. This gives the fuel 2 octane ratings, the weak figure is used in the fuel's name. So for instance, avgas 100 is a 100-octane fuel when the mixture is weak, but a 130-octane when the mixture is rich. These two octane ratings are known together as the fuel's performance number or index, so avgas 100 has a performance index of 100/130. High-performance engines with high compression ratios require high-octane fuel. Engines with lower compression ratios can use lower-octane fuel. The grades of aviation gasoline currently authorized and available are avgas 100 and avgas 100LL. Avgas has a freezing point in the region of -58°C, and a flash point, which is the temperature at which the fuel vapor will ignite in contact with a flame, of -40°C or colder. It has a specific gravity of 0.72 at 15°C. Specific gravity is important, as fuel is delivered by volume, but pilots need to know its mass or weight, as the energy available from the fuel is dependent on its mass, not its volume. Avgas 100 is colored green and has a performance number of 100/130. Avgas 100LL has the same performance number as avgas 100, but it has a lower lead content. It is colored blue. MoGas, or motor gasoline, can sometimes be used in certain airframe engine combinations, but only under the conditions specified in Civil Aviation Authority Airworthiness Notices No. 98, 98A, 98B, and 98C. Because of the higher volatility and water content of MoGas, carburetor icing and vapor locking are much more likely to occur if this fuel is used. The subjects of carburetor icing and vapor locking are covered in detail in the piston engine series of lessons. Information and advice on the use of MoGas can be found in the CAA Safety Sense Leaflet No. 4B. Diesel piston engines use AVTER. This fuel is described in the gas turbine engine fuel section. Gas turbine-engined aircraft use kerosene fuels. These are heavier and less volatile than gasoline fuels. They are placed between gasoline and diesel fuel in the distillation process. The two main types of gas turbine fuel in use in civilian aircraft are aviation turbine fuel, or AVTER, and aviation turbine gasoline, or AVTAG. As with aviation gasoline, in the United Kingdom, the specifications for these fuels are issued by the UK Aviation Fuels Committee on behalf of the Defence Material Standardisation Committee. There are two grades of AVTER in use. Jet A1 is used in Europe and most of the rest of the world, whilst Jet A is used in the United States of America. Jet A1 is a kerosene-type fuel, with a nominal specific gravity of 0.8 at 15°C. It has a flash point of 38.7°C and a waxing point of -50°C. Waxing is explained later in the lesson. Jet A is a similar type of fuel to Jet A1, but it has a waxing point of -40°C. Gas turbine fuels are not dyed for identification. They retain their natural colour, which can range between what is termed as water clear to a straw yellow. AVTAG is known in civil aviation as Jet B. It is not generally used in civilian aircraft. It is a gasoline and kerosene mix with a nominal specific gravity of 0.77 at 15 degrees Celsius. It has a flash point of -20 degrees and a waxing point of -60 degrees Celsius. Because of the very low waxing point, it may be found in use at a small number of civil airfields in very cold climates. If a fuel sample is placed in a clear glass container and swirled vigorously, and the sample appears cloudy or hazy, then there could be one of two reasons for this. If the cloudiness appears to rise quite rapidly towards the top of the sample, then air is present. But if the cloud falls quite slowly towards the bottom of the sample, then water is present in the fuel. Having said that, a cloudy appearance usually indicates the presence of water. A certain amount of water is present in all fuel. The water, which is dissolved in the fuel, gives rise to a number of fuel system problems. As an aircraft climbs to altitude, the fuel is cooled and the amount of dissolved water it can hold is reduced. Water droplets form, and as the temperature is further reduced, the droplets turn to ice crystals, which can block fuel system components such as filters. A microbiological fungus called Cladosporium resinae is present in all turbine fuels. This fungus grows rapidly in the presence of water to form long green filaments which can block fuel system components. The waste products of the fungus are corrosive, especially to fuel tank sealing substances. The inclusion of a fuel system icing inhibitor, or FSII, in the fuel will help to overcome these problems. The inhibitor in common use inhibits the ability of the water in the fuel to freeze and acts as a pesticide which retards the growth of the fungus in the fuel. Jet A1 has FSII, but Jet A does not. As we have already said, water is always present in fuel. The amount will vary according to the efficiency of the manufacturer's quality control and the preventative measures taken during storage and transfer. Further measures can be taken to minimize water accretion once the fuel has been transferred to the aircraft tanks. If the fuel can be allowed to settle after replenishment, then the water droplets, being heavier than the fuel, will fall to the bottom of the tank and can then be drained off through the water drain valve, which is situated in a sump in the lowest part of the fuel tank. Once the fuel is in the aircraft tanks, the main source of water contamination is the atmosphere that remains within the tank. If the tanks are topped up to full, then the atmosphere is excluded together with the moisture it contains, thus minimizing the likelihood that fuel will be contaminated. Caution is required here. Filling up the tanks may prove an embarrassment later if the ambient temperature rises, as the fuel in the tanks will expand, and there is a danger it may spill out of the vent system. Filling the fuel tanks may also incur a performance penalty, as the aircraft may be too heavy to take off with the required passenger or cargo load, and some fuel may have to be removed. As a further precaution, in order to prevent any ice crystals blocking fuel filters and jets, the fuel may be passed through a fuel heater located on the engine, which uses hot air from the engine compressor to remove any ice crystals which may have formed in the fuel when it's cooler than 0 degrees Celsius. Some systems utilize a fuel-cooled oil cooler as well as, or instead of, a fuel heater. The fuel-cooled oil cooler uses the hot engine oil to warm the fuel and in doing so produces the added benefit of cooling the oil. A number of additives may be blended into the fuel either at the refinery or the airfield to improve the operating ability of the fuel. A lubricity agent is added to the fuel to reduce wear in moving parts of the fuel system components. Static dissipator additives partially eliminate the hazards of static electricity generated by the movement of fuel through modern fuel transfer systems. This would otherwise be a particular problem with the high flow rates generated during refueling and defueling. Corrosion inhibitors protect ferrous metals in fuel handling systems, such as pipelines and storage tanks, from corrosion. Certain of these corrosion inhibitors improve the lubricating qualities of some gas turbine engine fuels. Metal deactivators suppress the tendency, which some metals, particularly copper, have, to cause the fuel to oxidize. We are now going to talk about fuel waxing. This is something that happens to fuel when it is extremely cold. Do not confuse this with the water in the fuel freezing. Gas turbine fuel consists of many hydrocarbons, each with its own freezing point, so it doesn't become a solid at one temperature in the same way that water does. As the temperature of the fuel drops, the heavy hydrocarbons, which have the highest freezing point, freeze first and form wax crystals. As the temperature drops further, the hydrocarbons with slightly lower freezing points start to solidify, and so on as the temperature continues to fall. The waxing point of a fuel is the temperature at which wax crystals begin to form. Jet A1 has a waxing point of -50 degrees Celsius, so waxing is only a problem for aircraft operating for prolonged periods at high altitude in very low temperatures. The crystals can clog the fuel filter and interfere with the operation of the engine fuel control unit. The effects of waxing can be minimized by the refinery keeping the heavy hydrocarbons in the fuel to a low level. The temperature at which a liquid boils will reduce as the pressure on its surface reduces. As an aircraft climbs, the pressure on the surface of the fuel reduces, and with that reduction comes an increased likelihood that the fuel will boil and form vapor in the pipelines. The vapor locks that this effect causes can cut off the fuel supply to the engine, with the result that the engine will stop. Fuel booster pumps fitted inside the tanks can help to overcome this problem by pressurizing the fuel in the pipelines from the tank to the engine, pushing fuel towards the engine rather than engine-driven pumps sucking fuel from the tanks and further reducing the pressure. Specific gravity, or SG, is defined as the ratio of the density of a given solid or liquid substance to the density of water. Or, to put it more simply, it is the weight or mass of the liquid divided by the weight or mass of an equal volume of water. So in the example shown here, we have 1 gallon of fuel in the left container, and it weighs 8 pounds. In the right container, there is an equal volume, 1 gallon of water, and it weighs 10 pounds. The specific gravity of the fuel is then 8 divided by 10, or 0.8. Specific gravity has no dimensions. The higher the specific gravity of a fuel, the greater will be the mass or weight of fuel for a given volume. And conversely, the lower the specific gravity, the less will be the mass or weight for any given volume. The specific gravity of fuel varies inversely with its temperature, so, depending on the storage conditions, the specific gravity of the fuel supplied to an aircraft may be different from the standard value. On modern aircraft fuel systems, this usually makes little difference, as fuel in the aircraft tanks is measured in mass or weight rather than volume, with the fuel quantity measuring system compensating for changes in fuel-specific gravity. However, if a high fuel load is required, it may not be possible to get sufficient volume of fuel on board for the required mass if the specific gravity of the fuel is low. That is the end of the lesson. The tables listing the characteristics of the various fuel types are shown on screen. Remember that ice crystals formed from water in the fuel are prevented from blocking the fuel filter by heating the fuel upstream of the filter using either hot air or oil. In this short lesson, we will examine the various methods used for storing fuel on board an aeroplane. The fuel is carried in or on the aircraft within tanks, which can be integral, rigid, or flexible. Integral tanks are made by sealing during manufacture the insides of the wings and, depending on type, the horizontal stabilizer and the center section torsion box between the wings to provide large volume fuel storage. The advantage of the integral type tank is that there is little extra weight added to the aircraft as the tank is formed from the structure already required. All modern large passenger aircraft will have this type of tank. A rigid tank is a sealed container mounted in or on the aircraft wing or fuselage. Rigid tanks are installed in a compartment designed to accommodate the tank. They are typically of metal construction and may be removed for inspection, replacement or repair. The aircraft does not rely on the tank for structural integrity. These tanks are commonly found in smaller general aviation aircraft. Rigid tanks may be fitted externally, on the wingtip for example. They may be made of metal or of a composite construction. Flexible tanks are reinforced rubberized bags installed in a section of the aircraft structure designed to accommodate the weight of the fuel. They are sometimes referred to as fuel bladders or bag tanks. The bladder is secured by means of metal buttons or snaps inside the compartment. Many high-performance light aircraft and some smaller turboprops use bladder tanks. They are also often fitted in military aircraft, as they are less likely than the other two types to split on impact, and they can be effectively self-sealing in the event of minor battle damage occurring. All larger aircraft fuel tanks have baffles fitted inside them. Baffles are fitted within the tank to restrict the movement of the fuel and minimize the large inertial forces generated when the fuel surges during aircraft maneuvers. Some aircraft may be fitted with baffle check valves, which allow the fuel to flow inboard but restrict its flow outboard towards the wingtips during maneuvers. Fuel tanks also incorporate vents, a gauging system, water drains, and filler caps. In larger aircraft, the tanks will also have booster pumps, high and low-level float switches, and pressure refueling valves. These components will all be explained in detail in later lessons. The main points to be taken from this lesson are that aircraft fuel tanks can be integral, rigid, or flexible, and that baffles are fitted in the tanks to minimize fuel surges during aircraft maneuvers. Remember that some aircraft may be fitted with baffle check valves, which allow the fuel to flow inboard but restrict its flow outboard towards the wingtips during maneuvers. In this lesson, we will look at fuel distribution systems. The aircraft fuel system is designed to store and deliver fuel to the engine fuel system. It must be capable of delivering more fuel than the engine can possibly use in its most critical phase of flight, so that the engine is never starved of fuel. Big jets, such as the Boeing 747, can burn as much as 10,000 kilograms per engine per hour during the takeoff phase. Here is a diagram of a simple, single-engined light aircraft fuel system. The fuel tanks are rigid tanks fitted in the wings. They are filled by an open-line refueling pipe through a filler cap on top of the wing. The fuel is drawn from the tanks by a mechanical or electrical fuel pump. Through a hand-operated tank selector, which allows the pilot to use the fuel from either the right or left tank, or turn off the supply completely. The fuel then passes through a strainer, which filters out any foreign objects and debris before being delivered to the engine carburetor. Piston engines often need to be primed with fuel prior to engine start. This is achieved by use of a hand-operated priming pump, which takes fuel from the filter housing and delivers it to the engine inlet manifold. The fuel system is monitored for contents using simple float-operated level sensors, and fuel pump operation is monitored by a fuel pressure gauge. Drain valves allow any water in the fuel to be removed before flight. Multi-engined gas turbine aircraft have more complex fuel systems to cope with the extra problems brought about by high-altitude operations, the use of multiple fuel tanks, and the need to feed the fuel to more than one engine. The fuel tanks are usually integral tanks in the wings. Many modern aircraft may also have a center tank, a tank in the center section torsion box between the wings. Some aircraft types also have fuel tanks in the fin or stabilizer, as well as being used to increase the fuel capacity. This fuel may also be used to change the position of the aircraft's center of gravity. There are a number of components and subsystems common to all multi-engined aircraft fuel systems. We will now look at these in some detail. The fuel tanks are fitted with a vent system. The purpose of the vent system is to allow the air pressure above the fuel in the tank to equalize with the ambient pressure. The areas above the fuel in each tank are connected together by a vent pipe. The ends of the vent pipe terminate in small vent surge tanks located at each wingtip. The vent surge tanks are vented to the atmosphere. The vent surge tanks are there to collect any liquid fuel which might get into the vent system during unusual maneuvering or because of overfilling of the fuel tanks. Any fuel caught in the vent surge tanks is returned to the main tanks either by gravity or by the operation of a pump. Some systems have float-operated vent valves fitted, which close to prevent liquid fuel entering the vent system. The EASA regulations require that when a fuel tank is full, a minimum of 2% by volume of the tank capacity is free of fuel to allow the vent system to operate correctly. If during refueling the fuel reaches this level, then the high-level float switch or volumetric top-off unit will close the refueling valve. As the aircraft climbs, the air pressure reduces. This in turn reduces the temperature at which the fuel boils, leading to excessive vaporization of the fuel. To help prevent this excessive vaporization at altitude, and to give a positive pressure of fuel to the pumps, ram air may be introduced into the vent system to partially pressurize the tanks in flight. This is normally done through ducts on the underside of the wings. Fuel booster pumps are normally fitted in pairs in each tank to pump fuel from the tank to the engine. They are a necessity in high-altitude aircraft to prevent bubbles forming due to cavitation or low-pressure boiling at the inlet of the engine-driven fuel pump. Each pump has a non-return valve associated with it to prevent fluid flowing back through the pump to the tank when the pump is switched off or has failed. Booster pumps are typically centrifugal pumps driven by 115-volt AC motors, providing a low pressure of between 20 and 50 psi with a high flow rate. There may also be a suction feed pipe to allow the engine-driven fuel pump to draw fuel from the tank in the event of a double booster pump failure. In the event of a double booster pump failure in one main tank, the aircraft emergency and abnormal procedure checklist will invariably limit the aircraft to a maximum operating altitude to prevent fuel starvation due to cavitation or low-pressure boiling, causing vapor locks at the inlet of the engine-driven fuel pump. Filters or screens are used to prevent any debris in the tank being drawn into the fuel booster pumps. The booster pumps are fitted in a feeder box in the bottom of the fuel tank. This box is sometimes referred to as a collector tank or surge box. The feeder box should remain full of fuel at all fuel levels and aircraft altitudes. This allows the booster pump to be continually submerged in fuel, thereby preventing them from being starved of fuel and keeping them cool. Electrically operated engine fuel shutoff valves, or low-pressure cocks, are fitted to allow the engine to be isolated from the fuel supply. Cross-feed valves and pipes form a cross-feed manifold, which enables fuel to be fed from any tank to any engine. In this example, there are only 2 fuel tanks, so only one cross-feed valve is required. As we have already said, many aircraft have a center fuel tank. In this example, the fuel from the center tank is pumped into the cross-feed manifold on both sides of the cross-feed valve. The aircraft may also have a fuel tank located in the fin or stabilizer. In our typical system shown here, the fuel from this tank is pumped into the center tank for distribution to the engines. High-level float switches are used to automatically close the refuel valve when the tank is full during refueling, while low-level float switches are used to maintain a required minimum amount of fuel in the tanks during fuel jettison or dumping. Each fuel tank will have a fuel drain at the lowest point in the tank to allow water to be drained from it. In the event of the fuel tank being overpressurized due to a malfunction, a relief valve may be incorporated to prevent structural damage to the tank. The system is completed with the addition of a refuel manifold, which allows all the tanks to be pressure refueled from a single point. Shown here is the fuel tank layout on a typical two-engined aircraft. The only difference to what we have seen so far is that the wing tanks are split into outer and inner sections. The fuel pumps are in the inner section. The outer section remains full until the inner has reached a predetermined level, at which point the outer section fuel is transferred by gravity to the inner. Keeping fuel outboard in this manner helps to reduce wing bending stress. On the screen now is the pilot's fuel control panel and a schematic fuel system diagram from a typical twin-engine passenger jet. The control panel shows selector switches for each main tank booster pump, accompanied by associated low-pressure warning lights which illuminate if the pump should fail or be switched off. The center tank pumps also have switches and warning lights associated with them. Suction valves in the main tanks allow the engine to be fed by gravity or suction by the engine-driven pump in the event of both booster pumps failing in one tank. There is a control switch and indicator light for the crossfeed valve. The light is illuminated when the crossfeed valve is open. There is a temperature sensor in the number 1 tank, which will transmit the fuel tank temperature to an indicator on the control panel. The engine fuel shuttle valve is closed by the operation of a fire handle for that particular engine. In some aircraft, it is also opened and closed by the selection of the fuel switch during the normal engine start or shutdown procedure. The fuel valve closed lights illuminate when the associated fuel valve is closed. The auxiliary power unit, or APU, takes its fuel from the number 1 tank via a suction bypass valve if there are no booster pumps operating, but it can be fed from any tank if a booster pump in that tank is selected on. The APU shutoff valve is typically operated by the APU automatic start or stop sequence. There are indicators which illuminate when their associated low-pressure fuel filter bypass valve opens due to a filter blockage. This filter is downstream of the fuel heater. Fuel from a pressure refueling system is fed in at the refueling station and dispensed to the fuel tanks as required. Defueling is achieved by opening the manual defueling valve. The booster pumps can then be used to pump fuel into a tanker. The normal sequence of fuel usage after takeoff would be to use the center fuel tank first, followed by the wing tank fuel. This sequence again helps to relieve the wing bending stress. The operation is achieved semi-automatically by switching on all tank booster pumps. Since the center tank pumps operate at a higher pressure than the main tank pumps, fuel is used from the center tank first. When its booster pumps can no longer pump fuel from the center tank, any remaining fuel can be moved to the number 1 tank by operation of the center tank scavenged jet pump. The main tanks will now feed their respective engines. The cross-feed valve allows both engines to be fed from one wing fuel tank, or one engine to be fed from both wing tanks. Fuel imbalance in flight between the number 1 and number 2 tank can be corrected by opening the cross-feed valve and then switching off the pumps in the tank with less fuel until the correct balance is achieved by supplying both engines from the tank with more fuel. It is important that this sequence is followed exactly, as there is a danger of starving an engine of fuel if the fuel pumps are switched off before the cross-feed valve is opened. When the correct balance is achieved, the previously switched off booster pumps are switched on again first, and then the cross-feed valve is closed. Again, it is important that this sequence is followed. This will restore what is known as tank-to-engine configuration, that is, number 1 tank feeding number 1 engine, and number 2 tank feeding number 2 engine. This diagram shows the fuel system from a modern, extended range, twin operational performance standards, or ETOPS, aircraft. It is very similar to our previous system, apart from a few additions to improve its reliability. The center tank is split into 2 parts, but it operates at all times as a single tank. The cross-feed valve is duplicated to provide redundancy. Normally, both valves move together as one. There are 2 shut-off valves in the fuel line to the engine. The spar valve shuts off the fuel as it leaves the tank system, and the engine fuel shut-off valve shuts off the fuel at the engine firewall. The APU has a DC electric fuel pump, which will switch on automatically if the APU is operated with no booster pumps operating. This pump will also automatically start, and the APU isolation valve will open to allow the DC pump to supply fuel to the left engine for rapid restarting in the event of a double engine failure. Some aircraft types have a fuel dump or jettison system fitted. This system is required if the maximum landing mass of the aircraft is significantly less than the maximum takeoff mass, and landing at the higher mass would compromise the structural integrity of the aircraft, or if the aircraft cannot satisfy the discontinued approach climb gradient required by the EASA regulations at its maximum takeoff mass. In an emergency, fuel can be dumped to reduce the mass of the aeroplane to its required landing mass. The fuel dump system consists of fuel dump pumps in each of the tanks from which the fuel is to be dumped, connected by pipes to fuel dump master valves and dump outlets. Typically, there will be a dump master valve on each wing at the outboard trailing edge to enable the fuel to be dumped safely with no danger of it entering the aircraft or any of its systems. On older aircraft, Fuel dumping is controlled from the pilot or flight engineer's fuel control panel. On modern aircraft, the pilot has a selector knob which allows him to select the amount of fuel to be dumped or the amount of fuel to remain. The fuel dumping process will be automatically stopped when this level has been reached. If operation of the flaps or slats will cause the fuel being dumped to impinge on the airframe, a placard must be displayed warning the pilot not to operate the flaps or slats during fuel dumping operations. It would be clearly undesirable to dump all of the fuel in the aircraft, and safeguards must be in place to allow a minimum amount of fuel to remain. EASA regulations stipulate that the minimum amount of fuel remaining after dumping must be sufficient to enable the aircraft to climb to 10,000 feet and thereafter allow 45 minutes cruise at a speed for maximum range. This minimum fuel quantity is calculated at the design stage, and the low-level float switches in the main tanks are calibrated to stop the fuel dump if this level is reached. That is the end of the lesson. Here are the main points you should remember. The fuel vent system uses ram air to pressurize the fuel tanks to help prevent vaporization of the fuel. The fuel booster pumps are 115-volt AC motor-driven centrifugal pumps, and they operate at pressures of between 20 and 50 psi. Their purpose is to supply a head of pressure to the engine-driven fuel pumps in order to prevent cavitation or low-pressure boiling causing a vapor lock at the inlet to the engine-driven fuel pump. The booster pumps are fitted in a collector tank or feeder box or surge box in the bottom of the fuel tank. This allows the booster pumps to be continually submerged in fuel, thereby preventing them from being starved of fuel and keeping them cool. The cross-feed valve or valves allow the fuel to be fed from any tank to any engine. Remember that when commencing cross-feeding, the cross-feed valve is opened before the booster pumps in the low tank are turned off. And when cross-feeding is complete, the pumps are turned back on before the cross-feed valve is closed. The purpose of the high-level float valve is to shut off fuel to the tank during refueling when the tank is full. Fuel dump or jettison systems are required on aircraft types where the maximum takeoff weight is significantly higher than the maximum landing weight. The fuel dump system must automatically stop dumping fuel when a defined reserve quantity of fuel is reached. This lesson will look at fuel quantity measuring systems. Fuel quantity can be measured by one of two methods. Either the volume of the fuel can be measured, or the mass or weight of the fuel can be measured. Volume measurement can be achieved by having a float in the fuel tank, attached by a suitable mechanism to a variable resistor. The cockpit gauge is normally an ammeter, calibrated in gallons or litres in a circuit with a resistor. As the fuel level decreases, the resistance increases. This leads to a reduction of current in the circuit, so the indication on the ammeter decreases. The gauge is calibrated to show the correct fuel quantity with the aircraft in straight and level flight. This system is normally restricted to light aircraft. It has two major drawbacks. Firstly, it is subject to maneuvering error. That is to say, as the aircraft's attitude changes, the indicated fuel quantity will change. Secondly, this type of system cannot compensate for changes in the specific gravity of the fuel. So, as the fuel gets colder, the indicated quantity will decrease, and vice versa should the fuel temperature increase. On modern gas turbine-engined aircraft, it is important that we measure the fuel on board the aircraft in terms of weight or mass rather than volume. There are a number of reasons for this. Firstly, it is important to know the weight of the fuel in the aircraft for airframe performance reasons. And secondly, the energy in the fuel is measured by weight or mass, not volume. So the pilot needs to know the weight of the fuel that he has available. Measuring the weight or mass of the fuel is done by having variable capacitors in the fuel tanks. The capacitive method works by supplying the two plates of a capacitor with alternating current. The current that flows in the circuit now depends on four factors: the level of the voltage applied, the frequency of the supply, the size of the plates, and the dielectric constant of the material separating the plates. In our circuit, three of these factors are fixed, and the fourth, the dielectric constant, is variable because the dielectric consists of fuel and air. A dielectric consisting of fuel will allow more current to flow in the circuit than a dielectric of air will. The level of current flow will therefore be proportional to the volume of the fuel in the tank. By measuring this current, we can know the volume of the fuel in the tank. If the temperature of the fuel drops, the volume of fuel in the tank will decrease, causing a drop in the current. The opposite will happen if the fuel temperature increases. The dielectric constant of fuel changes when its specific gravity changes. If the specific gravity of the fuel increases, more current will be allowed to flow in the circuit, and similarly, if the specific gravity decreases, the current flow will decrease. When the volume of a fuel reduces because of a reducing temperature, its specific gravity increases, and vice versa when the temperature increases. The system is designed so that these two changes cancel each other out. The capacitor type of system is therefore able to measure the mass rather than the volume of fuel. There is, however, still the problem of attitude error. To compensate for changes in attitude, the capacitive system has a number of capacitor probes in the tank connected in parallel to average the measurement of the fuel in the tank. In this way, as the attitude changes, a fuel level increase is sensed by one capacitor and a decrease is sensed by another. This enables the system to give an accurate indication irrespective of the aircraft attitude. On older aircraft, with analog fuel quantity gauges, if the fuel tank's capacitive gauging system fails, it does so in a manner to draw the attention of the user. A fail-safe circuit is incorporated which drives the gauge pointer slowly towards the empty position in order to prevent the indicator showing that there is more fuel in the tank than there actually is. Some systems also incorporate a test switch, utilizing the fail-safe circuit. When the test switch is operated, the indication moves towards empty, and when the switch is released, the pointer should move back to its original position. On more modern aircraft, the digital gauges are controlled by a fuel quantity indicating system, or FQIS computer. This computer monitors the system for any failures and generates appropriate warnings. In the event that the electrical fuel quantity measuring system fails, or if there is any doubt about the quantity of fuel on board, aircraft are fitted with a simple manual backup system to determine the quantity of fuel on board before flight. One method is to use a dipstick in the top of the tank, but of course this exposes the user to the dangers inherent of walking on high and possibly slippery wing surfaces. Another method is the dripstick. This is a calibrated hollow tube which is withdrawn from the undersurface of the tank through a fuel-proof aperture. When the top of the tube becomes lower than the fuel level, the fuel will drip through the tube, hence the name dripstick. The volume of the fuel in the tank can be established by reference to the calibrations on the tube. The disadvantage of this system is that the user's armpit soon becomes saturated with the fuel dripping from the pipe. A more user-friendly version of this system is the dropstick or magnetic level indicator. This system uses a rod calibrated to show the level of the fuel in the tank. The rod is fitted within a tube sealed from the fuel in the tank. Around the tube is a magnet supported on a float. The magnet moves up and down the tube with the fuel. The tip of the rod is also fitted with a magnet. When the rod is lowered through the tube, as the two magnets line up, their fields attract each other, and resistance to further movement will be felt. These systems all establish the volume of fuel in the tank. The weight or mass can be calculated provided the specific gravity of the fuel is known. Many aircraft have tables for doing this. The fuel system instrumentation on a light aircraft will consist of contents and pressure gauges as shown here. On large aircraft, it is necessary to provide more information than this to the crew. On older aircraft types, the fuel control panel is usually in the form of a mimic diagram with flow bars and lights to indicate flow. More modern systems have electrically presented schematic displays. The diagram here shows a typical Airbus system display. Modern Boeing aircraft have similar displays. The temperature of the fuel in each tank is shown here. This is important information for monitoring the system for fuel icing or fuel waxing. The fuel tanks are shown schematically, with the mass of the fuel in each tank being displayed. The wing tanks are split into inboard and outboard sections. In this instance, the outboard tanks are empty, as is the center tank. These symbols are used to indicate the position of the main tank outboard to inboard transfer valves. In this case, they are open. When closed, they look like this. These symbols are used to depict the fuel booster pumps. The line in the box is vertical when the pump is operating, as seen on the wing tank pump indications, and horizontal when the pump is switched off, as demonstrated by the center tank pump indications. The cross-feed valve indication is in line when the valve is open and cross-line when it is closed. The engine and auxiliary power unit shut-off valve indications operate in a similar manner. The fuel used by each engine since startup is displayed here. And finally, there is a readout of the total fuel on board here. That is the end of the lesson. Remember that light aircraft may have a fuel quantity measuring system consisting of a float attached to a variable resistor. The two problems with this system are that the indicated quantity of fuel will change when the specific gravity of the fuel changes, and the system will give erroneous indications during maneuvers. Most large aircraft use a capacitance type of system, which uses the difference between dielectric qualities of air and fuel to measure the quantity of fuel in the tank. This type of system is unaffected by specific gravity changes. And by using numerous detectors in the tank, it does not suffer from maneuvering error. In this lesson, we will look at how aircraft are refueled, and at the regulations that help to keep the refueling operations safe. Light aircraft are refueled by removing the tank filler caps in the wing upper surface and pumping fuel from the dispensing unit into the tanks. This is known as the overwing method. The quantity of fuel delivered in litres or gallons is indicated on a gauge on the delivery vehicle. Practically all modern jet-engined aircraft are pressure refueled from hydrants or delivery vehicles through underwing refuel and defuel coupling points. The operation is controlled from a single external refuel control panel. An example of an external refuel control panel for a jet-engined aircraft is shown here. This particular aircraft has 3 fuel tanks. The quantity of fuel in each tank in thousands of kilograms is displayed here. The blue high-level light will illuminate to indicate that the high-level float switch has operated to close the refuel valve because the tank is full. Each fuel tank has a 3-position refuel valve switch. The switches are guarded to the normal position. With its switch in normal, a tank's refuel valve is controlled by the automatic refueling computer. The open position opens the refueling valve unless the tank is full. In this case, the high-level float switch or volumetric top-off unit will close the valve and the associated high-level light will come on. In the shut position, the associated refuel valve will remain closed. The 3-position mode select switch is guarded to the off position. With the switch in this position, the refuel system is de-energized and the refuel valves are closed. With the switch to refuel, the refuel valves can be controlled either by their individual switches or the automatic refueling computer. With the switch to the defuel transfer, the transfer valve will open to allow fuel to be pumped from the tanks back into the tanker. The amber open light will illuminate. The test switch is a 3-position switch, spring-loaded to the center off position. When it is held to the high-level position, operation of the high-level float switches or volumetric top-off units is tested. If they are serviceable, the blue high-level lights will illuminate. The lights position tests all of the lights and puts 8s in all of the quantity windows. The pre-selected fuel quantity is shown in this window. It can be changed using the rocker switch. The total fuel on board is shown here. The end light illuminates when automatic refueling is complete. Having connected the refueling supply, the normal method of refueling would be to pre-select the required fuel load. Ensure that all 3 refuel valves are in the normal position. Then move the mode selector to refuel. The automatic refueling system will now refuel each tank in the correct sequence to achieve the pre-selected fuel load. When refueling is complete, the pre-selected and actual windows will read the same, and the end light will come on. The mode select switch should now be returned to the off position. Fueling vehicles and hydrants dispensing AVTA are identified by prominently placed labels with the words Jet A, Jet A1, or Jet B, depending on the grade, printed in white on a black background. Fueling vehicles dispensing avgas are identified by prominently placed labels with the word avgas and the grade, for instance 100 LL, printed in white on a red background. Before refueling an aircraft, fueling zones must be established. These zones will extend at least 6 meters or 20 feet radially from the filling and venting points on the aircraft and the fueling equipment, covering all areas where fuel vapor may be expelled during refueling. Within these zones, the following restrictions apply. There must be no smoking. The use of photographic flash bulbs or electronic flash equipment is not permitted. If the exhaust of an auxiliary power unit or APU, which is required during the refueling operation, discharges into a fueling zone, then it must be started before filler caps are removed or fueling connections made. If the APU stops for any reason during refueling, it should not be started again until fueling has ceased and there is no danger of igniting the fuel vapors. Electrical ground power units, or GPUs, should be located as far away as practically possible from the fueling zones and not be connected or disconnected while fueling is in progress. Only authorized personnel and vehicles should be allowed within the refueling zones, and their number should be kept to a minimum. Before refueling commences, the aircraft must be bonded to the fueling equipment using dedicated wires and clips. This ensures that there is no electrical potential difference between the components which could lead to sparks. Reliance must not be placed upon conductive hoses for effective bonding. When overwing refueling, the hose nozzle must be bonded to the aircraft structure before removing the tank filler cap. Similarly, any funnels, filters or cans that are used must be bonded to the aircraft. Plastic funnels or pipes must never be used. When underwing pressure refueling, the mechanical metal-to-metal contact between the aircraft fitting and the nozzle end eliminates the need for a separate hose end bonding cable. There are a large number of precautions which need to be taken during refueling. here are the precautions that are most relevant to the flight crew. In case the aircraft settles on the landing gear as the weight increases, all ground equipment should be moved clear of the underside of the aircraft. The main engines should not be operated. Strobe lighting should not be used. All torches and lamps used within the refueling zones should be either certified as being flameproof or be of the intrinsically safe type. The sequence of refueling the aircraft tanks can adversely affect the aircraft's center of gravity position, particularly if the correct filling sequence is not followed and/or the aircraft has a vertical or horizontal stabilizer tank. If any doubt exists about the correct refueling sequence, the aircraft refueling manual must be consulted. Fire extinguishers should be located so as to be readily available. There are a number of special hazards that need to be looked out for during refueling operations. Aircraft should not be refueled within 30 meters or 100 feet of radar equipment, either under test or in use, in either aircraft or ground installations. If the landing gear is overheated, the aerodrome fire service should be called and no refueling should be carried out until the heat has dissipated. Extreme caution should be exercised during electrical storms. Fueling operations should be suspended during severe electrical disturbances in the vicinity of the airfield. To reduce turnaround time, and for security reasons, the regulations permit airline operators of fixed-wing aircraft to allow passengers to embark, disembark, or remain on board during fueling operations, provided the following safety procedures are followed. It is not permissible to refuel fixed-wing aircraft with less than 20 seats while passengers remain on board. Passengers must disembark if avgas or Jet B is being used. One qualified person must remain at a specified location during refueling operations with passengers on board. This qualified person must be capable of handling emergency procedures concerning fire protection and firefighting, handling communications, and initiating and directing an evacuation. Crew, staff, and passengers must be warned that refueling is about to take place. Seatbelt signs must be off. The no smoking signs must be on together with the interior lighting to enable emergency exits to be identified. Passengers must be instructed to unfasten their seatbelts and refrain from smoking. Sufficient qualified personnel must be on board and be prepared for an immediate evacuation. If the presence of fuel vapor is detected inside the aircraft, or any other hazard arises during refueling, fueling must be stopped immediately. The ground area beneath the exits, intended for emergency evacuation and slide deployment areas, must be kept clear. When passengers are embarking or disembarking during fueling operations, they should do so under the supervision of an airline official, and their route should avoid the fueling zones. These safety procedures are important. Spend a moment studying them. Click to continue when you are ready. That is the end of the lesson. The points to remember are that light aircraft may be refueled by the overwing method, but practically all transport jet aircraft are pressure refueled through a single point, normally under the wing. When overwing refueling, the hose nozzle must be bonded to the aircraft structure before removing the tank filler cap. Here on screen is a list of the safety precautions that should be taken during refueling. Click to continue when you have finished studying them. Finally, here is a summary of the regulations governing refueling with passengers on board.